Oops. What's this? Ah, okay, yeah, that's live.
That works.
Very good.
It's fairly recent, so yeah, we're good.
So we still have like 6 minutes to go. Let's do some painting here. Mona Lisa.
Fairly recent.
Okay, I hear echo.
Yeah, sorry, that was me listening to the live stream.
Okay. By the way, you can hit the trash can if you realize that your contribution to this art painting is not very valuable.
Yeah, green one.
And you can start from scratch. There's a pig.
I think maybe we haven't seen it. The real painting.
Okay, I think you're now just adding more hair. So let's try to compare a bit. Let's stop here. So that would be the original painting. And it's close.
Yeah, not too bad. I mean,
beautiful.
Yeah.
I can't tell which is what.
Yeah, right. I think some requirements are not respected, but I think we're there.
In particular, this pig here.
Yeah, maybe.
Is missing.
But
there's a shape. Yeah, it could be located here. Good. Feel free to put some more graffiti here. While you're doing that, you're being recorded and live streamed. And actually, it's a good time here to put also the big blue button recording on. So be careful. You'll be watched.
You're already watched on YouTube. So. Good. Beautiful. Make a screenshot.
So in the land of UTC, it's going to turn 11 o'clock soon. It's a connection test, so feel free to open your cam. Anyone, everyone, open your cam. We can try to crash the server already at that stage. And also open your microphone. Because now Red is going to introduce you to an activity that it's become mandatory for all these workshops, because we have accumulated so much energy by staying home all this year that needs to get out. So hand over to you, Red.
sort of yes activities.
Can't hear you. Red, we can't hear you. I can see your lips moving.
Okay, and now? Can you hear me
That's
now?
good. Yep.
Okay, super, great. All right. So you mean for me to go to the next presentation, right? The warm-up. Or do you want to do the welcome? Warm-up. Okay, warm-up. Warm-up.
Well, there's a small countdown, and then we all scream. I think this was on the next slides. If you just go further, yeah.
All right, everybody. Yeah.
But what are we going to scream? That's the question.
Yeah. So we have to scream something. So everybody turns on your microphone. You can stop right now to turn on the microphone. So feel free to scream anything. You know, the thing that worried you the most the last year, the thing that made you the most happy, or just something that means open source to you. And we have a countdown, okay? So you have that word or anything in your head. Maybe it can be gibberish, I mean, nothing, you know, like, blah. So it's up to you. So you have 5 seconds, take a big breath in, and then shout, okay, we're going. 5, 4, 3, 2, 1. I want to hear you.
Okay, redo it.
We do it again. Okay.
I could only hear myself, and my neighbors could hear me.
3. No, I mean 5, 4, 3, 2, 1. Ignition!
Open
All right.
Good.
Okay, got it. Thank you, guys. You can applaud yourself. Do not hesitate to feedback the speakers. We're here for that. So we're here to listen. We're here to interact. That's the main thing we want to do here. So all the meetings you had this last year where you could not chat, you could not talk, this is not this one. So do not hesitate. All right. So Arthur, the welcome note. Want to go for it?
Okay. So is it now default?
Yeah.
Which one is it?
Yeah, it's not.
There's 2 defaults. So it's this one.
That's the good one. Yeah.
You added this hashtag OSCW21. This is the hashtag.
This is for digital archaeology. You know, if you want to share things, use the hashtag. So later we can find it.
Good. So this is the welcome. And let's look a bit back. And we started this 2017, so that's 4 years ago. And this was started in ESOC in Darmstadt in Germany. And yeah, this was the first time. So feel free to put your name, tag your name if you find yourself in the crowd. And okay, you can just put your marker there. That would be sufficient. And we see. And those who are not on that picture, they can, group maybe here. Okay. So there's some. Let's try 3 years ago. Where did we go? Where was it? Exactly. It was in. So we moved from ESOC to ESAC. Just changing one letter. Same thing here. It was in in ESAC, near Madrid, Spain. Beautiful setting. Nice people. Was amazing.
Every year, nice people.
And then,
Then
the year after, where did we go? Great. It was in Athens, the heart of Libre Space Foundation. And it is a bit more crowded on this picture. Okay, you're adding yourself virtually. Very good. Okay, so. And then last year, where did we go? Nowhere. We stayed at home. We were staying online. Okay. And in fact, this year, we're home again. So we'll go for the Open Source Cubesat Workshop 2021. And we have, being home these 2 years, we have saved so much CO2 footprint that for the next workshop, I think we can really go for a blast, and we can have it in Australia. What do you think?
Oh gosh, yeah. Japan?
Let's go in Antarctica.
And so I suggest again we do we switch on our camera, and we try to make a group picture, right, on the very first day before we even start the conference. So everyone switch on the camera, please, and I'll take a picture.
We'll hide the presentation, right? More. Turn on the camera.
So we have 60 users online, more than 60 users. No robots online, just a live stream.
Not of that we know of.
And yeah, we can have. Everyone has a camera, right? Everyone is dressed up, at least the upper part, like me. So there's nothing stopping you from switching on your camera, except maybe the fact that it's live streamed on YouTube, and the whole world is watching you. And particularly your boss, who doesn't know that you're attending an online conference right now while you should be working.
It's work.
Okay, I think that's it. We take a screenshot. So, smile.
You have to say 3, 2, 1.
Oh yeah, right. It's just a test. Well, everyone is free to also take a screenie.
In the meantime, I take screenshots without.
Okay, let's try this again. 3, 2, 1.
Is it good?
Maybe the one came a bit as a surprise. People were still moving. Anyway, later we cut this out from the live stream, and then we edit it, and it's gonna be great. Hi everyone. Okay, let's continue the presentation. Where was it? Here.
Oh, sorry.
Did you do?
Go ahead, default.
There's 2 defaults, which is very irritating. So, okay. I'd like to introduce a bit the organizers behind this workshop. Of course, the workshop is only as good as all the participants. So you're very important to be here. To your time to attend this workshop is very much appreciated. And these are the people that did all the work in the background so that you can enjoy it now. Maybe feel free, Nicoletta, Pierre, Serkos, Mantos, Red, to say a few words, Vasilis, myself. But we will be guiding you throughout the workshop. So, yeah, feel free to contact us anytime.
Yeah, we're here in the chat. We'll try to answer your questions, even the technical ones. So do not hesitate. Yeah. Super happy to be here, guys. Super happy to see you all here. That's so cool. Thanks for the hat. Yeah, it's so sunny.
Okay. Somebody scratched my face. Great. Good. Here's some random notes. I didn't know how to put them, but I should mention that we are recording right now, and we are also streaming on YouTube. And this conference, this workshop is going to be 2 days, and it's about 7 hours per day, which is quite long. I mean, sitting 7 hours in front of your computer is long, but hold on. That's what we're doing actually every day at work. So I think it's still okay. We can do it. But if you feel you're getting hungry or you need to go to the toilet or you just need a break, like a power nap, do it, please. Yeah, don't hesitate. And because it's your home. It's your home. You can do whatever you want, right? Except maybe naked dancing in front of the camera. But apart from this, do what you want. It's your home. We're invited. We're your guest. Thank you very much. And difference to last year is that this year we are one track, one room. So there's no confusion. Stay in this room. You will see all the presentations. And that's why it's a bit longer maybe than last year. But we will survive. Now let's have a quick look at the program. So Thursday, Friday, we are in this welcome right now. And after that, we're going to have our first talk session. And these talk sessions in blue, they are about 4 to 5 talks each session. And then there's a break afterwards. And I'll tell you a bit about this break in the next slide. So it follows this pattern: talk, break, talk, break, talk, break. Okay. Then we have a keynote in the afternoon, not at the beginning of the conference, but later on. The reasons will become very obvious when I tell them to you. Then we have this lightning talks to boost up everyone again for the wrap up, which takes place just like at the end of the day. And then there's an open hangout. On the Friday, it looks very similar, but it's all a bit mixed up. And in addition, we're going to have on the Open Source Cubesat workshop, we're going to have a workshop. Amazing. We have a workshop at a workshop. And I think that's just great. Talks, break, talks, and maybe we can introduce another break here before we do the closing, because the talks, the later the talks, the better they are. So don't miss the Friday afternoon talks. And then, believe it or not, there will be a closing to these 2 days eventually. Okay, about the talks. I would suggest that we have only the speakers, the camera on. Maybe that's good that on the live stream that people see who's giving the talk. I mean, if you're shy, you don't need to open the camera, but you can put a mem there or something. But it would be great to see you who's actually talking, just like on a real stage. And in particular, those who are not talking, maybe you can then switch off your camera, because last time we had people, making a coffee, eating a banana or something, and it's a bit irritating.
Yeah, if I'm like that when after speaking.
But of course, during the question and the open discussion part, switch on your camera, switch on your microphone. So it's like this: 12 minutes of talk, 8 minutes of open discussion, constructive, friendly discussion, feedback. Tear up the project, tear up the talk, but in a nice way. Yeah, I was Red. If you want to add anything, just jump in.
You said everything.
Yeah, I think everything is great. We're good to go.
Then the breaks. That's a bit special this year, or different, let's say. So after the talk session, we have always a break. It's going to be 20 minutes long. We're going to open breakout rooms. And the pattern is like this. So we're going to have as many rooms as talks plus 1. So room 1 is talk 1. I think the logic is clear here. And then there will be another room And the last room, so the highest number room, this will be the lounge. You can just go there and everyone can talk with everyone, just like in a big lobby. Let's see how this works out. Yeah. And yes, in the break, you can switch and join these rooms as you like. You have this 20 minutes. And the idea is that you can even get more information from the talks that you are really interested in and talk to the speakers. So the speakers should go in the room of their talk. Good. Then the keynote is from Dr. Pauline Four, and she is assistant professor at Cal Poly. The topic is, well, in a nutshell, it's about open source and space education. And she's in the West Coast, so that's why we have this keynote in the afternoon, which is her morning. And we are really looking forward to this keynote. Lightning talks. Red, correct me if I'm, yeah. So it's going to be 4 talks.
4 minutes talk. At the end, we have the yes, as usual. I'll guide you through that. Don't worry. And it's 4 minutes. You have your own 4 minutes. You do whatever you want. You can talk only 1 minute and just request feedback from everybody, or just talk 4 minutes straight and get the feeling of everybody. Up to you. Yeah. And this is we welcome other contributions, meaning that we have a program with the first lightning talks which were submitted. But if you have an idea during the workshop or you want to reach out to everybody, we'll be happy to give you those 4 minutes. Of course, to the limits that we can do. So do not hesitate to reach out to me, and I'll try to make you stick inside this program. Thanks.
That was the lightning talk from Red, and about the lightning talks. And okay, the hangout tonight is like this. It's a bit like open-ended. Grab a beer or something, and it will be in this main room, of course. And then you can, I think at the beginning we will discuss on what topics we want to discuss, and then we establish the rooms accordingly. And again, you can join those rooms as you like. So if you want to talk about ground stations, then you would go to this room. If you want to talk about I don't know, anything, maybe the weather or
blockchain and space,
then you would go to this other room. Okay. So we still have, about 3 minutes before we start with session 1. If you have any question or feedback, you can scream hooray into the microphone.
Oh, sure. There was the warm-up thing. Yeah, just
the warm-up.
Yeah, I mean the map.
Over to you.
Yeah, no, don't worry. Just a quick one, because it's only 3 minutes. So we already warmed up in the beginning. We screamed. We were free drawing. We know how to do that. You can applaud each other. Don't worry. Okay, well, which I just wanted to reach out. Like, which one do you prefer? You know, like Star Wars or Star Trek? If you had to choose only one. Yeah. Okay. Star Wars. Yeah, I see. Star Trek. I see like the Federation sign. I see this. Right. Okay. I see like there's a lot of Star Wars scribing or striking out. Cool. Okay. I'll stop. 68 is good. Thank you. But now, please pin down where you are on Earth. Please try to use a fine pencil, so we have some kind of a feeling where you are right now. George, of course, you're in Antarctica. Sorry, we can't zoom. Just don't stay in the middle. Nice. Okay, can you all move apart if you did already, or move on the side, move your cursor on the side. Nice. Some people are on other planets, you see? Yeah, very good. Yash. Oh, right, nice. Is it Argentina? Chile, Peru. Chris, you're okay. Michael, Chris.
Yeah, and we're doing this on really early times for the US people, so we should probably do this also in the afternoon. It will change completely.
Yeah, we have to. Yeah, definitely. Good point. Thank you, everyone. Thank you. So now session one will start. So you're ready. Stay open, stay empathic. That's the goal. And share your ideas. Don't censor yourself. That's the most important. So Arthur and I think Pieros, you're leading the first section. LF, Arthur and LF. So back to you guys. Yeah.
Okay, that was a warm-up. Very good. Not too hot though, so I feel still a bit chilly, but it's okay. It's I take the screen. So welcome to the first session of talks. We're going to have 4 amazing talks, and we're going to start. And I'm going to chair the session together with Elkos, who happens to also give a talk during the session. So I
can subscribe for 2 megahertz bandwidth and split it between several users. So every user can connect in parallel and set up a socket and receive only one small portion of the data, like 48 kilohertz out of these 2 megahertz bandwidth. And they can receive this data concurrently, right? Internally, I'm using frequency escalating filter block, which does bandpass filtering, then moving into the baseband, and then decimating the output. So that would give very small network usage over here for the clients in comparison to the whole 2 megahertz bandwidth. This setup can be quite useful for remote locations when you, for example, want to set up a Raspberry Pi with RTLSDR and antenna somewhere else, and then access it from the internet, because you can stream this raw IQ data very efficiently. It's just a very small portion of it. And you can support multiple clients. But I'm mostly interested in this project for my other project, R2 Cloud, where I monitor satellites and receive the data from them. So I was wondering if I use this SDR server, can I increase the number of observations and whether I can increase the number of data I'm getting from the satellites? Because that was the goal if I monitor these 2 megahertz at the same time. And on its own, SDR server is not enough to increase the observations and increase the number of data for passive monitoring, right? So the SDR server is the first step. The next step was creating an auto-scheduler that can help maximizing this utilization. So there's several things to consider for this auto-scheduler, that we can schedule 2 meters and 70 centimeters observations at the same time, right? Because they're so far apart, much more than 2 megahertz. And then even the 70 centimeters band is a bit wide. So there are many satellites which transmit on different frequencies within these 70 centimeters, and the more than 2 megahertz between them. The other thing to consider is that all satellites are equal. That means when I schedule observations, I should evenly distribute observations for each satellite. And generally speaking, this is an NP-complete task to solve. So I need to optimize schedule so that I can utilize hardware even more efficiently. So as the first thing to solve this, I try to split the range into several bands. So let's assume we have several satellites and all of them require some bandwidth. So we know center frequency and the bandwidth for each satellite. And when I sum up, I have a range of frequencies I need for the list of satellites. And then I split this range into several bands. They might overlap a bit, but generally they just go one by one. And then the SDR server can hop from one band to another one. So then this autoscheduler can schedule observations in each band separately. So as you can see on this picture, there are several satellites transmitting on different frequencies. Try to put this in very colorful squares. So these satellites, for example, they transmit on very close frequencies and they overlap in time a bit, but they also can overlap in frequency. But since they are falling on the same band,
In embedded computing, we identified several open source business models. One example, there are examples and parallels on these models depending on the niche you're talking about. Either you take the generic stuff like business to business open source like Android and how Couple operates, or you take other open source business models. It always depends on how you want to operate and what kind of resources an entity would like to use on a certain project. Most of the projects we identified are software. There are some hardware projects, some standards, and some online services, but they are few. On the other hand, mostly the projects we identified are focused in design and analysis and downstream applications, which is something we expected actually. During the course of the project, we performed several sub-activities together with partners like friends from Polyastro. For example, this sub-activity refers to constellation design system. It's really interesting that you can actually see it online. It's web-based. There's also an IQ modulator. Actually, is using off-the-shelf system on chips. How to have embedded DACs and actually streams and transmits IQ data. It's really interesting, especially because it's an open hardware project and an open source software project. And also interestingly, the hardware and software needed, the software is free, but the hardware needed is just commercial off-the-shelf hardware. You can order it almost everywhere. And there was also a sub-activity that focused on creating in exporting model from electromagnetic simulation to use in open EMS using FreeCAD, which is really interesting because you can say two different pieces of free software being able to share data. There's also SatNOGS Tiny, which is a really interesting approach on building a SatNOGS client, considering that all the needed systems are in just an embedded system SBC, and you can actually get your own simple, limited, but effective SatNOGS ground station, considering the cost. More or less, OpenSatCom was a way to figure out whether or not open source development models are relevant to the satellite communications industry and in general in space. But the thing is that there are constraints to such models and have to be understood before someone proceeds into adopting them. On the one hand, on the other hand, one has to take into account that if you pick a proper open source development model, which is really affected by your licensing scheme, you will be able to find a proper way to build a sustainable project that will be used by several other people too, which is really important. I'm open for any questions, ideas, or anything else you would like to share.
Okay, Elkos, you got me there. You still have a few minutes left, but okay. Finish a bit earlier. We can have more questions and some more troubleshooting. Seems like this year you have a bit of an internet problem. Maybe a lot of people do using the internet now. Questions. I prefer you scream with the mic. You can also raise hands, or as a last resort, if you're really one of those shy guys, then write it in the chat. Good. Well, have you conducted any marketing researches?
Well, yes. When you say marketing research, you may mean that whether or not we have contacted the industry and asked whether or not they could provide some input.
Andre is asking that, yeah.
Yeah. So, yeah, the thing is that we did, our partners at Keynote did, but to the extent of their reach, they had really few responses to provide any meaningful statistical output. So, I believe that there is information to be taken from that, meaning that a different approach should be taken. And but I believe that such information would be useful not only for us, members of the open source community itself, but for the space industry too.
Yeah, then Glenn is asking, can you say more about the tiny SatNOGS client?
Sure. Yeah, the thing is that for people that are familiar with SatNOGS, SatNOGS has to have a set of software running usually on a Raspberry Pi or x86 machine, preferably a Raspberry Pi. It's cheaper to do it and more cost efficient power-wise. The thing is that even a Raspberry Pi with an RTL SDR is a bit costly for some people. So we started thinking whether or not we could use one of the numbers embedded ESP32 machines that are used everywhere nowadays in the do-it-yourself space, and with a LoRa submodule, because these chipsets can also do other stuff, not only LoRa, in order to get some data and in order to create a rudimentary station. On the other hand, as you may know, SatNOGS is based on GNU Radio, and it's using SDRs in order to decode LoRa. The thing is that there is a legal gray area, more actually a black area, considering that LoRa PHY is not actually, it's protected by the IP of the creators of LoRa. So if you can actually decode LoRa using an RTL SDR, theoretically, but you're in a legal gray area. And we would like to put people on that condition too. Okay, considering that LoRa is in a legal gray area in space anyway. But yeah, we can open that discussion sometime, some other time.
Okay, also there are some comments that your microphone is difficult to understand, Elkos, but actually that's the voice of Elkos. It's like that. So, well, just kidding. I think your microphone has a bit of a overtune, but good. We also have some other people with microphone issues. I think Red is setting up other ways, other channels that we can at least get the audio. So we have to have a separate channel for the audio using different technology, and the video and the slides. Let's see. We're going to be surprised how this is going to work out. But now we go to the next presentation of Josh. I'm going to load it. And so Josh is a third-year undergraduate student from India. He's in computer science. And so he has all this computer background. In addition, he also joined the Polyastro project some time ago. Maybe you can tell more, since how long, a couple of months or years. And I think that's amazing story to hear, because this is basically what brought you into, well, you said that you learned about space using that project, and in particular astrodynamics, and then you also contributed to it. So that's really the best case scenario. Yeah, you take, you give, and it's all about sharing. And your topic is about space situational awareness. So that's very relevant for all of us, because once we go up as astronauts into space, we want to make sure not to get hit by some other satellites, or maybe even more importantly, when we send our open source CubeSats into space, we want to make sure that they're not going to be hit by these nasty closed source proprietary CubeSats and other satellites that are flying around there. So your talk is gonna shed some light on how to prevent that. And I'm handing over to you the presentation role, and over to you,
Okay.
Yash.
Yeah, thank you, Atu, for the introduction. So, hello everyone. I am Yash. I was a Google Summer of Code student at Libre Space Foundation, and I was working for the project Polyastro, where we added a couple of event detectors. And I would just like to give a brief overview of the different event detectors that we added and the results that came out of it. So, even before we start talking about the work that we did, space events are everywhere. There might be various kinds of events, especially when the satellites have been launching into space with increasing number. There are lots of probabilities of satellite crashings or different kind of events happening. There might be beneficial events. For example, in the case of satellite communication, if you want to communicate between two different ground stations, then you can have a satellite that uplinks and downlinks data so that you can communicate between those two stations. But there's also a negative side of this. There can be disastrous events where a satellite can collide with other satellite, or maybe there's junk in space, or it might just collide with the attractor on its attractor surface. So in such situations, we might want to have an event detection system that's robust and also swift. And so the work that we did during the summer was to search for peculiar points that is directly based on the classical orbital elements of the satellite. So the whole thing now boils down to finding out zero crossings of the event function. So this event function would potentially be a function of the classical orbital elements, and our goal is to find when did the event function cross this zero mark, as we can see here. And the propagator that we use for this event detection was the Cowell propagator, which is one of the propagators in Polyastro. There are also a lot of other propagators, but we use this because it allows us to model deviations from the standard two-body problem. And there's also one more reason that it is the only function that uses SciPy's solve IVP function. So it was the go-to choice for us to do. And the solve IVP function essentially just solves the two-body ordinary differential equation. And each of these events would also have a terminate attribute and a direction attribute. The terminate attribute would signify whether we want to stop the propagation of the orbit once that event has been detected, or we want to continue propagation of the orbit. And the direction attribute would specify whether the event function is going from positive to negative or from negative to positive. So the direction attribute also adds some sort of a physical meaning to the whole event detection mechanism. And the approach that we used was a point-by-point check procedure. By point-by-point, I mean that we check for event detection at each instant of time during the propagation. So we have an orbit, we propagate, and then again check for the event, and then again check for the event at each point of time. There are critics of this method deeming that this can be inefficient and slow at sometimes, but as we will see later, we leverage a specific package called Numba, because of which this is not so much of a problem in our case. And ultimately, the goal of Polyastro is to be useful for interplanetary missions. So it works with any attractor. So it's not just specific to Earth. You might have a satellite that orbits around Mercury, for example, and then you can still apply the events that we have developed. And just to give a brief overview of the module, as is common for all the modules in Polyastro, submodules in Polyastro, we have this two-body module that's a high-level interface, and we have the core module that does the fast computation that was talking earlier. This core module would make use of the Numba package, because of which these calculations can be done a lot faster. And the user is on this side, where it will access all of these Cowell propagator, which itself calls which calls solve IVP inside it. And so when we go from this high level to this lower level module, we need to remove the units, and when we come back, then we attach the units. So that just gives a brief overview of how these modules have been designed. And now let's explore the events that we added during the summer. So I've included the altitude and the lithobreak event on the same slide because they are more or less similar. So the altitude cross event would just detect when your satellite crosses a specific altitude from the attractor surface. For example, as we can see, this blue line signifies that the terminal attribute is set to true. So when it's, for example, at a threshold altitude of 50 kilometers, then the orbit stops. and if it's orange, then it will just go on till the end, till how much time you want to propagate the orbit. And the special case of this would be a lithobreak event. Just to clarify that this wasn't added during the summer, but we did change the interface of it so that it now becomes a subclass of the altitude cross event, because it's just a special case of this altitude cross event where the threshold altitude is set to 0. So for example, we know that the Messenger spacecraft was launched by NASA, and it was deliberately crashed into its attractor surface, and so that it could understand the chemical properties of the spacecraft and etc. And so in such cases, this lithobreak event might have some use cases. And there might also be other examples like defunct satellites that crash into Pacific Ocean or any oceans on Earth, where this lithobreak event might be useful. And the next event that we added was the latitude crossing event. It detects whether a satellite crosses a specific latitude on its attractor. And again, to clarify a terminology, that this latitude we are referring to is the geodetic latitude in the case of Earth, or in general, the planetodetic latitude. That's just an equivalent version for any attractor. And we do account for the flattening of attractor, because we know Earth is not purely spherical. So we do account for that. And so one might think that since we have added this latitude crossing event, so what about the longitude at detector? Now, since we know that the longitude increases or changes in the east-west direction, we also have to account for the rotation of Earth. So at the time we were doing this latitude crossing event, we didn't have to account for that, and it was relatively easy to do. But for the longitude detector, it becomes a bit more involved. So we are taking some time to include this in polyastro. Then the next event that we added was this eclipse event. We account for both penumbra and umbra regions of the eclipse. And again, it's important to mention the assumptions and the considerations that we used. We do not account for the flattening of attractor in this case. For example, we do not assume that, we assume that the sun and the planets are totally spherical in shape, but we do account for the movement of bodies. As we know, the sun and the planet would all revolve around this common point called as the solar system barycenter. So we do account for this, and we recalculate the position vectors of the sun and the planet at each instant of time. So it allows us to handle this scenario. And in fact, this movement of bodies would be is in fact essential so that it can be used during the propagation of orbit itself. And to just show the eclipse geometry, that the previous diagram that I showed was just an extended version of those 3 points. But here we can see the sun, the central planet, and the satellite is here. We can detect whether it enters a particular region or it exits out of a particular region. And it just shows the geometry of the whole situation. And the next event that we added was this node crossing event. It essentially checks for the inclination of the orbit itself. So it's similar to the latitude crossing event in terms of the description, that we now check for whether the altitude, whether the orbit crosses the ascending or the descending node. And it essentially boils down to checking whether the inclination of the orbit is 0 or not. The next event that we added was the line of sight event. Again, to clarify our terminology, the line of sight here refers to the line of sight between 2 different satellites. So it's not between a ground station and a satellite, for example. And again, the approach that we used as of now is a simple trigonometric manipulations, due to which we could have some inequalities in the angles, and we could detect whether the LOS occurs or not. And this might have importance in inter-satellite communication. And let's say we have this LOS event inbuilt in a system, so we might do further sophisticated analysis on top of that. For example, we could have a radar system technology that could find distance between 2 different satellites once we know that they are in the line of sight. And the whole point of all of these events is to give an interface so that people could use it for further analysis or more sophisticated treatment as well. And the work was not done yet. We needed to validate all of these events. And for this, we used the ORCID library. Unfortunately, it's written in Java. But again, thanks to the ORCID Python wrapper, we could use Python code to test both ORCID and the polyastro orbits. And the methodology for this would be it's simple. We just propagate both the ORCID and the polyastro orbits and match the time of the event occurrence. And the result that we got was that the time difference is more or less than 2 or 3 seconds. we have, as of now, we have set a threshold of 5 seconds at the maximum because both of the ORCID and polyastro event detection mechanisms are different. So there might be some sort of differences in both of the implementation. But as of now, it serves as a good first implementation. And so if we want, let's say, sub-second accuracy or something like that, then we might also consider making this more accurate and more robust, for example. And I also want to say that there are other approaches to event detection, and we wanted to have those in the scope of polyastro, but there are also other event detection approaches that are done in literature. For example, we could do an anomaly detection approach on the time series that is generated from the two line element sets of the orbital elements. So for example, in this Lee and Chen paper, they classified these anomalous points that are shown in red as the potential points as potential events. And so this graph shows the semi-major axis plotted in terms of time. So there's this one approach, and there are also several approaches that we could use. For example, we might have weather satellites, or we might have satellites that are measuring the temperature in its surroundings, and we could use event detection mechanisms in a whole lot of different scenarios. But the goal of event detection module in polyastro was to have the simple event detection mechanisms that could be used for any satellite that has a predefined orbit. And the work is not over yet. There are lots of event detectors that we are thinking of, some of which are already in progress. For example, the satellite visibility event, for example, it checks whether a satellite is visible from a ground station or not. And also the attractor surface visibility, it checks whether a satellite can see a particular point on its attractor surface or not. So these are events that are currently in progress. And we're also thinking of further events, for example, whether two satellites would collide or not. So these are a bit more ambitious for us right now. We were thinking of these events, but we couldn't do in the time frame of Google Summer of Code, but we hope to add them soon in polyastro so that we get more variety in the event detection modules that are being added so far. And thank you. That's what I had to say about the event detection mechanisms. We are obviously looking for suggestions, ideas, and bugs, and we would love to hear any suggestions or ideas that you might have. You might come into the Polyastro's issue tracker and just put down your suggestions or ideas that you might have, ideas for events that are going to be added or events that have already been added, and we're also looking for that. And finally, it's a big thank you to Libre Space Foundation for giving me this opportunity to work at Google Summer of Code, and also to my two mentors, Juan Lu and Jorge, because it wouldn't have been possible if they wouldn't have guided me throughout this journey, because I had a slight knowledge of orbital mechanics, and they really helped me not just in the code contributions, but also in the non-code contributions. And yeah, I would also like to say thank you to them. Yeah, so thank you for this attention. I'll be happy to take any questions that anyone might have.
Thanks, Yash. My immediate reaction is amazing. I was thinking that when I heard about event detection, I was first thinking that it's maybe some specific events like the orbit crossings or so. But what you have presented here is basically you're covering everything that is relevant to space operations and that flight dynamic department at ESOC, for example, that they're producing. So like the eclipse events and the orbit crossings, the orbit anomaly. So it's really exhaustive, and well, I'm really interested to maybe we could run a comparison test for the cluster mission, which is going into eclipse in the spring and the autumn each year. And Flight Dynamics is predicting those events when we're going into eclipse, and then we have to prepare them and the satellites and recover them after they come out from eclipse. So we get from Flight Dynamics the timings of these events. And it would be interesting that if we provide you the orbits of those satellites if you could kind of, to compare those values and see, because we actually see the reality. It's not a simulation. We see that the satellite's being powered off and don't receive any sunlight anymore. And in fact, some while ago, we had to correct. We had the radius of the Earth taken into this calculation, but it turned out that the eclipse events were always a bit off from the prediction. And it turned out that we had to account also for the atmosphere. So we added a 20-kilometer radius to the Earth, artificial radius, and then it worked. So
yeah. So polyastro has a whole lot of different atmospheric models. So apart from the standard two-body problem, we could add a whole lot of this atmospheric models and then probably get closer to real-life situations.
very good. So we have a question from the audience. Milenko is asking if this has already been integrated in polyastro.
Yeah, this has already been integrated in polyastro. It's in the early stages right now, and it is probably also bound to change. But yeah, we had a release yesterday of polyastro, so it's now you can just do pip install and you would have this events ready.
Ah, okay. Great, just in time.
Yeah.
M1 is asking or saying that it's a good presentation, and how's your planning for the re-entry control?
For
the re-entry prediction.
re-entry prediction, is it for the Eclipse one?
Re-entry control, it even says. So maybe you have to interpret. You're free to interpret the question as you like. Also, yeah, re-entry, atmospheric re-entry.
Oh yeah, that can also be done in principle. So whether, for example, if you have a satellite far away from the planet, its atmosphere, then yeah, we could in principle be able to do that. There will be some sort of a factor that would help us sort it out in that sense.
Okay. Then also, I mean, I mentioned Eclipse, but Fernando is also asking about just like the AOS and LOS, so the visibility of ground stations. I assume this is also possible to calculate.
Yeah, in fact, we are working on this. We are working on some. We are working on this event detection, but we are facing with some edge cases because of which we couldn't do this, and that was observed while validating against ORCID. We found out that the event detection times were matching were almost 99%. There were just 1% of cases where it doesn't match. So yeah, we are working on that, and this ground station visibility event is soon to be merged, expected to be merged. Yeah.
Okay, very good. Thank you, Yash. We are going over to the next presentation. And that one is going to be a bit of an experience now and a challenge, because Rashika and Boris, they're both sitting at Sensors, which is hosted at the Paris Observatory. And I'm receiving on all channels information about how we're going to, make this presentation now become a reality, because the fact is they're really on a hill in Paris, where they have a good overview about Paris, but they have, seems like, no connection. So there's no cell phone. I've been there 2 weeks ago, and in fact, there's almost no cell phone connection, because you're looking at a space, at the sky. You don't want to be disturbed by so profane activities like calling someone. And also their VPN is blocking them, their audio at least. So I think they really want to make sure there that people focus on their work. And we are going to find some way around this. Let's have a look. What is the information? Maybe someone can join me on the stage and tell me how we're going to do it. I heard something about Mumble. Meantime, Ms. Mantos is telling me something, but it's not related. Good.
We should. Hello.
Vasilis, hi.
Can you say hello?
Yeah, perfect.
Hello. Hello. Hi. Can you hear me?
Rashika, I can hear your voice. Great.
Good.
So I assume it works like this, that red, but is kind of using the account of Vasilis and he's connected to you. Anyway, you somehow figured out how it would work. Someone is also controlling the presentation. So I will hand over to you, just a few words. Rashika has a master in aerospace engineering at ISAE Supaero. It sounds Spanish when I pronounce it, but it's actually French. You're also, you're going to present docs and open source software that you're working on, and also you have good background on model-based system engineering. You're doing this at Census. So without further ado, I open the floor to you, and please go ahead.
Thank you for the introduction, Arthur. Okay, so I'm Rashika Jain and I'm a research engineer at Census, which is the space pole of PSL University, hosted at the Paris Observatory. Today I'm going to talk about our in-house software called Docs, which is an open source software to make space mission profiles. Thank you. So in the last decade, the use of Cubesats has significantly increased, and we are using them for missions ranging from the low Earth orbit to interplanetary missions. This has created new demands of mission profile analysis tools. By mission profile analysis, I mean not only computing the trajectory, but also computing the system budgets. For example, the analysis of pointing, power, and data volume. So some tools already exist in the market, but they cannot either perform the complete mission profile or they are not affordable for everyone. So to overcome this gap, we are developing Docs, which is which stands for Design and Operation Cross-Checking Services. It's an open source software, and it has it will be composed of 7 modules, which will compute the trajectory, the quaternions, the intervisibility, data link, and the onboard power of the satellite during the mission. So all these modules are developed in Python, and Docs is fully compatible with Ubuntu and Windows operating systems. In addition, we also have a remote service that has been recently developed. Can you move to the next slide? Thank you. So an additional advantage of Docs is that it is compatible with the VPS, which is a software developed by the French Space Agency to animate and visualize satellites in a 3D environment. So till now, only 3 modules have been developed. Can you move to the next slide? Thank you. So till now, only 3 modules have been developed in Docs. They are propagator, intervisibility, and EPS. So first, I will talk about the propagator. Next, please. So the propagator. No, one previous slide, please. Okay. There is some.
I think there is an embedded object.
Okay, so in any case, okay, so the propagator module of Docs computes the deep space trajectories for cruise, rendezvous, and proximity operations. It is a very versatile module, as you can add numerous gravitational and non-gravitational perturbations. In gravitational perturbations, you can have point masses as well as complex bodies using spherical harmonics or any other complex models. Besides, at Docs, we believe that the user should not be asked for the time step. So we have recently implemented an adaptive time step integrator called IES15, which adapts the time step very accurately, and you can compute the flyby trajectories with high accuracy as compared to the traditional Runge-Kutta methods. So yes, the next slide, please. Thank you. So And in addition to the numerical engine, we have also implemented a time step manager that is needed for modules like continuous propulsion. Why it is needed? So if you're using an integrator with a fixed time step and you have a time step equal to h, so on the left side, the time vector you see on the left side, it will look like that. But if you need to do some propulsion burns in between these time steps, so the integrator will totally miss that. So the time step manager modifies the time vector and inserts these time steps inside in the time vector. In addition, besides the propagator can be used by command line or the graphical user interface. On the right side, you see a graphical user interface, which is just a glimpse of the actual GUI. And it has multiple tabs that helps you define your inputs to produce a good trajectory. Okay, so before talking about the next modules, I will like to introduce the concept of EVTF. EVTF stands for event files, and they're used very often in space missions to structure the mission. Now, EVTFs are required for almost everything, and that's why we think in terms of EVTFs. And intervisibilities module is an example of this concept. So it computes the intervisibilities with sun and the ground station passes and produces an event file that you can see on the right hand side. Now, this event file basically tells you the events that are happening at a particular time. So you can see the ingress and egress to the ground stations in this file. Now, in this the intervisibilities module, we have used parallelization for faster computations, and in addition to that, the accuracy of this event file is tunable to a value of even 1 second difference. Okay, so the next module is energy power simulator. It takes into account the solar arrays, the configuration of the solar arrays, the cells and the battery, the modes of the mission, quaternions and the intervisibilities, and computes and the power on board the mission, and generates outputs as you can see in the picture. So this is an example displayed in VTS. So on the energy row, you can see that you can see the variation of your onboard power during the whole mission, and as soon as the energy goes below the minimum level, a flag is generated in red color. So this type of with this output, you can clearly see that you need to resize your energy power board, and it helps in basically the resizing of your Cubesat. Okay, as I told earlier that we have a remote service and we have recently started this. So it helps to compute the mission profiles using our server, and you do not require any installation of docs in your own system. Because of this, you also have faster computations. So it's very easy to use this remote service. You can just send an email at the given email address, and then our server creates an online repository for you, and then you can just upload your inputs and the configuration files, and you will have your results in a few minutes, depending on your test case. Now, Census also provides support to nanosat teams in the early phases of mission planning and designing. And we are currently giving support to some internal as well as external teams. Now, we use docs extensively for this purpose. And now on the top right, you can see a flow chart, or this is an MBSE architecture that we're using for a project. And on the leftmost side, we have the science inputs, and in the center you have many models that help structure the project. And you can see that docs is at the center of this project structuring. And then we produce outputs that are just some text files, the eVTF files like I told earlier, and they can be read and even displayed in VTS. So on the bottom, you can see an example of these chronograms in VTS. Yes, so these kind of outputs help the project teams in mission profile analysis, basically. To conclude, docs helps to structure your Cubesat project by computing the complete mission profile. We have a propagator that has a smart numerical integrator, and recently we also wrote a paper on this, which has been accepted in the IEEE Aerospace Conference and will be published in March 2022. It computes the intervisibility and the power, and we will be developing more modules in the near future. And the advantage of docs is that it is free and it is accessible for everyone. It's an open source software. And in addition, we also have a remote service if it's not compatible with your system. And in the future, we are making it faster and more user friendly, and we are developing the graphical user interface for the modules that don't have one. So to contact, you can message us at the given email address on the right side. And thank you for paying attention. That's it. If anybody has any questions,
thanks very much. Thanks very much. We heard you loud and clearly. So this worked.
Yes.
Okay, there's some time lag, but it was amazing, and we heard you, and we got the message, and yeah, we're open for questions now. So there was a clarification, MBSE, I mentioned this model-based system engineering. So that's basically everyone working, well, it's yeah, based on models in engineering rather than just exchanging documents. Maybe you can elaborate a bit on this. How do you?
Yes. Sorry. Could you please repeat the question?
The model-based system engineering. How do you see this as a future for the for Cubesat development?
Okay. Yes. So the idea behind developing these models is to help the science teams so that they can have an initial idea of of the system budgets of their mission before approaching a space agency, and they have more control over their own project than the space agency. So that's the idea of doing MBSE for the project teams.
Good. I see a question from Juan Luis. Can the propagator be used in standalone fashion? That means, does it have Python or command line API, or does it need to be used in docs?
No, actually, thank you for the question. Actually, all the modules are independent, and they can be used alone. So propagator can be completely used standalone. You need to have definitely Python if you're using it on your own system, and you can use it via the command line, or yes, thanks for the slide, and you can use it via command line or the user interface.
Okay.
And if you don't want to install it, we also have a remote service. Sorry.
Good. So you're providing this as a remote service for people who do not want to run it locally. I understand via
Yeah,
email.
exactly.
There was a question. So anyone can send an email?
Yes, yes. Anyone can send an email. Yeah, we need to just mention the tag in the subject server. Yeah, just below the email ID. And you will get a link from the server where you can upload your files.
Okay, let's try this out, and maybe if we do this all at once, we can really stress test your server and see what's
Yes, yes.
I also
That will
see
be
that.
good.
I also saw that you have this models very well modular models, and I mentioned it already last time to you that also because of the name docs, it might be interesting to Dockerize this whole thing, because then you can also
Yeah.
it's maybe easier for other people to set it up locally if they want to run it locally. I'm sure some people here in the audience, they have some Docker experience, and maybe Docker and Docs, that could be a very nice combination. And yeah, it's always good also to draw some connections with the other presentations. So before you, we had Yash talking about satellite events, and you were mentioning right now these event files. So satellite events,
Yeah.
event files. Is there a connection? Like,
Sorry, I did not, I could not attend the previous presentation because of the network issues, internet issues.
okay.
And so I will have to look into that if there is a connection.
Okay, so but these event files are to describe formally in kind of a protocol these events that are going to happen, and that could be anything like a ground station contact or an eclipse that's going to happen, and that would be also a machine and human readable format to
Yeah.
distribute this information.
Okay. Yes, that's right. That's correct.
Very good. I think we can make a connection here. Good. Then let's look at the clock. We have, yeah, we're coming close to the end of the session. Thank you very much, Rashika, and great that everything worked out.
Yes, yes, I'm happy.
Thank you.
Very good.
Amazing, amazing.
So yeah, thanks to the people working in the background to make this tunneling possible. So we managed to get into. Okay, I can hear some snakes. Now it's gone. All right. So that concludes the session. We had Andre talking about the SDR server and Elkos on the OpenSatcom. Yash was presenting the satellite event detection, and Rashika was talking about docs. And we're going to open now the breakout rooms. So let me manage presentation. I'm going to upload the break, and we're going to open the breakout room. So for the next 20 minutes, we're going to have an official break, meaning, but also that you can go and chat with your favorite talks. So room 1, SDR server, as I mentioned, and the room 5 is the launch to hang out with everyone else. And then we continue at 13 hours UTC. So I'm going to open create breakout rooms, 5 rooms, 19 minutes. Users can assign randomly by themselves. So of course the speakers would be great if those go into their associated rooms. See you in 20 minutes.
Ah, cool. I can hear you, Boris. Super, and I can see you on GT. Yeah, it's okay. Understood.
Hey, can you hear me?
Boris? Yeah. I mean, I can hear you from here. Can you hear me, Boris? Yes? Oh, super. Okay, perfect. So that's definitely some big blue button. Let me check. I think Montos has the thing. Hello, everybody. Welcome back. Welcome back to the channel. Let me just turn on the camera here. You know who's talking. Hello. Okay, I need a feedback from somebody else in the room. Tell me if you can hear me. Montos?
Hello, Red. Can you hear me?
Yeah.
We can hear you.
Super great. Sorry, those breakout rooms are always too short. I know. So welcome back to the main room. We're going to start with session 2, where we have Boris is going to talk about astrometry on OPSAT. Is that possible to have that on board OPSAT? Boris, can you hear us? Just a little check.
I can hear you.
Perfect. While Mantos is turning on your presentation, and I will.
No, I can't. I'm not a presenter.
Okay. You can.
Do you want me?
I can do it.
Okay.
Super. Thank you, guys. So Boris is the technical director of Census, which was formerly Ceres, right, Boris? Great. So the Observatoire de Paris, with us today. So Boris, take it away. You prepared an experiment for OPSAT 1, and you've been accepted, and this is just the beginning. And we'd love to hear about what it's going to be about astrometry on board OPSAT 1. So the floor is yours. I'm going to manage your slides. You can ping me to switch slide. Yes.
Sorry, is still muted?
Yeah, Arthur? Super.
Can I start?
Yes, you can go ahead.
Okay. So please note that there is a question mark at the end of the title of this talk. So can we make astrometry on board OPSAT 1? And that is still a question. So this is my. Okay, can you hear me or?
Yes,
all fine.
Yes.
Okay, I'm sorry, I was disturbed. So please next slide. I won't make a long introduction. So I just remind you that we are trying to focus on the next generation of CubeSat for science, and we target deep space CubeSat. Just for the context, so we are interested in providing support to scientific teams. Next slide. So one of the technology we would like to deal with and to master is to make astrometry with normal nanosatellite hardware. But astrometry can be very useful for various scientific applications, or also for various technologies like deep space navigation, or here on my example, it's for science. Here you've got a wonderful picture. I don't think you can get it from a nanosatellite camera, but you've got a wonderful picture of Jupiter and Saturn in the same field of view. Maybe if you go to the next slide, we put it in negative, and you can distinguish that we have moons of the planets, of both planets in blue, and stars in the background in red. And thanks to that, we can precisely determine some new confirmations or some new fits for physical models of the motion of the moons, and then it confirms or it details some theories that are behind. So astrometry is very the entry point of a lot of science. So next slide. Here in our case, I'm interested in improving the measurement we can get.
Oops, we lost you. Lost Boris. What is? Hey, Boris.
Oh, the sim.
Right here, you see. Yes.
So we lost you for 10 seconds.
Okay?
Yeah, we lost you for 10 seconds.
Okay. So my purpose at the moment is to test and characterize a new algorithm to improve the measured direction of a celestial body in the background that you can see in the picture as a blue dot here, and based on the measurements of the stars, of known stars that you've got also in the same field of view. And combining everything together is quite challenging on board, and we'd like to do that on board. On ground, it's a technique that is well mastered. Target, they reach accuracy at a milli-arc-second accuracy, but they do that on ground. I want to do that on board, and I want to do that with Cubesat hardware. So we target sub-arc-second accuracy at the best. So the algorithm behind, I won't detail it now because it's not exactly the message I want to tell you right now. So next slide. Yep. But the idea is, okay, it should be easy with the Cubesat hardware because typical Cubesat imager is an imager with a multiple degrees field of view, let's say a 10-degree field of view typically. Although it is specialized in Earth observation, so okay, we are about to look at the black sky. So let's see how it will behave. And we've got ADCS, so Attitude Determination and Control System, that provides an absolute pointing error at about 0.1 degree and attitude knowledge error between 15-30 arc-second typically. So we think, okay, we can point to the target we are interested in and expect some pictures of targets and stars. Stars indeed, because typical hardware claim that they are sensitive up to magnitude 6. And a star field of 10 degrees, so you can see that on the bottom right, a star field of radius 5 degrees, so diameter 10 degrees, yes, should provide a field of view with at least 10 stars up to magnitude 6, greater than magnitude 6, at least 10 stars. So, okay, we should have many stars in our field of view. Let's try an experiment with Orsat. I will talk about Orsat, and we'll make some statistics and see if our algorithm can make that solid and can improve this kind of accuracy. So Orsat is a very cool project by ESA-ESOC in Darmstadt. So Orsat 1 is a 3-unit CubeSat. They've got in the box, they've got a SEPP, which is a layer to interface to some hardware like the imager or the pointing systems. The pointing system is the AI, so ADCS provided by Berlin Space Technologies. So we've got reaction wheels. You can see on the top right the ADCS with a star tracker. We can distinguish at least 3 reaction wheels, maybe I see 4. We see magnetopters, and the star tracker claims to be sensitive up to magnitude 6, and it's pointed in the XY plane. And the imager on board is also provided by Berlin Space Technologies, is pointed to -z, so in the longitudinal axis. So that could be a problem, not to point in the same plane like the star tracker. Okay, let's see. The field of view is 10 degrees, so as expected. Also, maybe another challenge, it's not a monochromatic imager, it's a color camera, so with a Bayer pattern matrix, so alternating red, green, and blue pixels. but there are a lot of pixels, so 4 million pixels, and the raw picture is coded on 12 bit. So we suggested to use this hardware, and our experiment was selected. We got the ID number 156, and we know that we have first to characterize what we can do with that hardware. So our experiment is astrometry, but first, so we expect a foreground object. We use star fields, known stars, and we'll take one of the stars as the object of interest and we'll demonstrate our algorithm. That's fine. But in addition to that, because we want to characterize, we need to characterize the hardware, we'll have a good assessment of the stability of the platform. And my point, and thanks to Red, or because of him, in preparing this talk, I thought, okay, maybe we could have that as an open source project. Maybe we could have the characterization of the stability of the platform as an open source project. So I'm not talking with the agreement of Orsat team at the moment. So I'm just suggesting that we also have to see if they agree. But maybe if people are interested, we could do that all together as a professional amateur project, for instance. Next slide. Yes, so at first, with this hardware on Orsat, we need to see stars. Then Orsat team provided me with some pictures. Actually, they were very helpful. So we tried with 2 millisecond pixels, with 2 millisecond exposure time, then 50, then 100, then 120. Okay, then I started to post-process the pictures, and I see clearly that from one picture to the other, I've got the same hot pixels. So hot pixels mean that they are the same pixels bright on multiple images. So meaning they are dead. They are dead. And there are a lot of hot pixels. Okay, so maybe we can have other picture of stars. So, but no, they were cosmics. Cosmics are not dead pixels, but they are very numerous. So here you've got a spectrum of the pixels, and okay, yes, thank you, Red. You are right. You should push me to go a bit quicker. So bad news is we've got a lot of hot pixels that we don't care. We've got a lot of cosmics that we don't care. And the problem is that we don't see stars. But then, next slide, suddenly, one day, the Orsat team, and thanks to Vladimir and Dominique in particular, we have to see stars. So we exposed 500 milliseconds, and they wrote to me, okay, we start seeing something. So I think you can see three white dots on the left, and they are the same on the right. So different picture showing the same pattern of stars. Okay, so in order to see that, they had to clean rapidly the picture, and then maybe go to the next slide. And yes, indeed, maybe go to the next slide. So we've got the negative picture. Okay, so for sure we see stars this time. And Dominique went to astrometry.net, which is the reference to characterize an image of the sky. And indeed, we got a match with astrometry.net. It was confirmed. So next slide. And so I should see a star in this region of the picture, but I can't see it. So why is that? Next slide. Indeed, let's make a negative picture. We've got some pixels here. And next slide. Okay, now we can see it. So after cleaning the picture, indeed, we can see stars. They are really not as expected. We expected something very limited to 1 or 2 pixels, and we've got something that is spread over tens of pixels. Next slide. And once we see that, once we know that, so I made a post-processing, a systematic post-processing, and indeed, in this same picture, we could see up to 13, maybe 14 stars. Each star is diluted in many pixels. And if you make a total signal noise ratio of each star, so cumulating the signal that is spread over pixels, then indeed you've got bright stars. So the pity is that the brightest star here that is quite invisible is a magnitude 3.5 star exposed during 0.5 seconds. So if you know a little about astronomic picture, so it's just a crime to dilute so much flux and to make it invisible. Next slide. And so the reason is that these pixels were spread and were hidden in a range of the histogram that is above the noise, for sure, that is limited by the noise itself is limited by the red vertical line, and behind the green vertical line we've got 5 sigma signal, so meaning that it cannot be noise anymore. It just cannot be. So they are completely diluted in this region of the histogram. But okay, if we clean up the sky, the pictures, we can see them, and astronomy.net can also see them. And just come back a little. Astronomy.net tells us also the region of the sky with an exact match of the orientation of the field of view. So that's very interesting. So next slide. And if we go further, if we expose to 800 milliseconds with the same imager, then we can clearly see the drift of the satellite during the exposure time. But not only the drift, we can also see some kind of wobbling or a vibration, because transversely to the drift, we still have some pixels that receive signal. So that's probably not a good setup. We should limit ourselves to 500 milliseconds. But at least we've got a good setup to make astronomical pictures. Okay, next slide. So there is, in order to get the stars really visible and to characterize the field of view on the sky, I had to make a post-processing, which is a complicated one with a lot of cleaning. And after we have to tag astrometry.net information to put that in the picture and so on and process that. And it's partially manual. For instance, on the top, you've got a star as seen during the cleaning process. So this is the raw picture on the left, and you can distinguish a hot pixel on the bottom of this. Yes, this one here. And on the right, you've got a convolution of this star, which makes it much easier to see and to characterize. And on the bottom, you've got a cosmic, typical cosmic, that is heating the CCD from the edge. So that's why it's illuminating 2 pixels at the same time. But then on the convolution picture, it really looks differently. So that's how we can clearly distinguish both. So, but anyway, the process is quite boring, and it's quite long, complex, and partially manual. And we'd like to have this process conclude in VTS formatted file. So Rashika, in the previous talk, presented VTS displayer, which is a CNES software. Next slide. And indeed, we'd like to produce the results of this analysis as a VTS reconstructed mission in order to understand and to interpret what was the stability of the platform at the time we took the images and what we were exactly looking at, while the onboard ADCS was assessing some pointing. Okay, I got 1 minute. So we want to go up to this kind of post-processed products. Next slide. On our side, we've got a clean room, we've got some cuts, we've got a nanosatellite imager. It's not the same like OSCW. We've got reaction wheel. We could reproduce what's really happening in the Cubesat. So that's what we want to focus on with our hardware, with our large facility, and we think we can interpret what's happening on board. Next slide. And then on the post-processing part, I think we could share something, and maybe it will help OPSAT-1. For sure, it will help OPSAT-1. Maybe it will also help OPSAT-2 at the stage of the design. Maybe we can provide them with new specification. Tell them, okay, be careful, guys. You've got a real problem with the control law here because it was wobbling. What do you expect to do with the next generation? And so on and so on. We can also suggest shielding the imager and how much shielding we need because we can process this kind of pictures. And for everybody who is trying to design a CubeSat, I would say, please, when you buy your ADCS by Blue Canyon Technology, Berlin-Flex Technology, EasySpace, wherever you want, characterize your ADCS. Don't think it will work exactly as in your dreams. I call that Process Sky Pictures. It's a new project on the public gitlab.com, so you can access it with this QR code. If you want to join the party, please tell me, and we'll see if we can maybe offer this project to OPSAT a new generation of experiments, and we'll see if they are interested. Thank you, Red, for this great operation support.
Thanks a lot. Thanks a lot for your flexibility and yeah, we can upload you. I think this is great. We have a question from Andrzej. We'll just take one question, but please write down your questions so that Boris and Shika can answer the questions. The project around image acquisition and post-processing on CubeSats are surely groundbreaking. How can we make and contribute to this project sustainably, long-term and full-time, not as a hobby, but professionally, not pro-am, but more pro in the future, in the long term?
Well, no problem. I'm talking about pro-am because I think there is a broad audience in this open source CubeSat workshop. Oh, by the way, I called the release of Process Sky Picture, which is the first release, I called it OSCW. So just for you guys. So if it becomes famous in the future, then you can say, okay, I started working on that with the OSCW version. Well, just contact me, I would say.
Yeah,
just contact
exactly.
me.
I invite you, Andrzej, to contact Boris. And Boris, thank you again once more. And this is a great project. I hope I can use it also on my ground telescope, actually. That would be nice.
Yeah, why not? Why not? I hope you have less cosmics.
Yeah, right. Thanks a lot.
And you've got vibration.
See you soon. So on the next talk we have George. George, are you here? And I know you want to share your screen.
Hello. Yeah, I'm here.
Great. George Zakarelis is going to present IPFS Tiny. So IPFS stands for Interplanetary File System. And George is a big fan of decentralization. So peer-to-peer chatting over Bitcoin at day and and you know, IPFS at night for space. So
yeah, that's right.
yeah, right. So George, the floor is yours. I won't take
perfect. Would you give me the presenter rights?
Yeah, sure, Montos.
No, you have it, Red. You are the presenter.
Okay. But okay, George.
You should be. Yeah.
I have to find you in the list.
Okay, perfect. I'm sharing.
Great.
Should be seeing my slides, right?
Okay, it's coming up.
I'm trying, yeah.
Our rules are turning.
Is it okay? Should I start?
Oh, now it's okay.
Perfect, yeah.
All right, so welcome to IPFS Tiny. As you can tell, it's related to IPFS, and IPFS Tiny is basically LibreSpace's effort in bringing IPFS closer to embedded systems and space applications. So let's get straight into it. Before we start with IPFS Tiny, I will cover like two basic terms here, IPFS and IPLD. IPFS is the Interplanetary File System, which is like the whole solution of, it's the full package. And IPLD actually is a part of IPFS, but it's grown so much that it's now a different project. It stands for Interplanetary Linked Data. And it is actually the data model that IPFS uses to sort of specify data. So let's focus on IPFS. So IPFS is a distributed file system. This means that if you store data to IPFS, at the end of the day, anything related to your file your stored file will not live in one machine, but it will instead live across the network. And IPFS, in order to be distributed, it utilizes a peer-to-peer network, and they also use DHT. I think it's still Kademlia DHT, to sort of boost routing between peers and help peers make gossip, like learn where each block is stored. And another great, maybe the greatest attribute of IPFS is that it is content addressed. This means that in IPFS, whenever you request something, or a file basically, you never ever mention locations. You mention CIDs. CID stands for content identifier. And you basically, when you request a file from IPFS, this is all the content identifier, which is like the file identifier, is everything that you need in order to receive the data from anybody in the network. And you don't need to trust anybody in the network in order to receive that file. And this is thanks to IPLD. And IPLD defines data so that they're specified basically as a Merkle DAG. And I won't get deeper into what Merkle DAG is. So let's think of it like data represented as a graph that can verify itself, and a graph that will realize whenever a small tiny bit of its body changes. Merkle DAG has nodes, like a graph it is. Those nodes are self-descriptive, meaning that the file itself, but every other subsection of the file as well, can sort of describe themselves as to what they are and what they are storing, their file, their size. And self-descriptiveness leads to compatibility, both backwards and forwards. So like a file today in IPFS can be of a specific CID version, for example, CID version 0, which was the first version of files, so to say, in IPFS. Everybody now moved towards a new version of CID, CID version 1. It depicts files in a pretty different way, but the whole network is still compatible with CID version 0 just because of self-descriptiveness. And on top of that, due to the fact that it's a Merkle DAG, basically, files are self-verifiable. So this would be like what a picture of Earth would look like according to IPLD. So let's suppose we have a picture of Earth, and it is basically all this array of blocks, data 1 to data 4. So altogether they make up the PNG file, and IPLD will construct this small graph on top of the file, where you have basically the lowest layer to be like CIDs pointing towards the blocks themselves. So like CID, the leftmost CID is the one that corresponds to data 1. And recursively, working your way upwards, you build like intermediate fathers, and you end up at the end with one root father, which is like the CID of the file, and it is unique and deterministic for each file. Like if you regenerate the same file, if you represent earth.png again in IPLD under the same rules, of course, like for example, there are many different trees you can construct. Like this is a binary tree over the file, but you can also make other DAGs, like flat DAG, for example, where you would have one father and all the blocks would be immediate childs to the root father. So if you have the same file and the same rules for the graph construction, you will always get the same CID, and this CID is unique for the file. So let's get into IPFS Tiny. IPFS Tiny is basically a C++ Tiny implementation of IPFS. And it is mainly embedded friendly. And this, I guess many people know what it means. In a nutshell, I would say it's like maintaining respect towards the system resources. This mainly extends towards memory allocation. You don't want to do dynamic memory allocation, and this renders you a little bit disabled because there are many many libraries in C++ that don't have this behavior, so you have to like find libraries to replace, like STL, for example. You need ETL instead, or for protobuf, the same thing. You need libraries that are embedding friendly. And yeah, that's one of the main attributes of IPFS Tiny. Also, it is meant to work on all architectures. So IPFS Tiny has the right abstraction layers, so it can work on an ARM system or an x86, and I will cover a bit more on this later. And it is also file system agnostic. So, like to locally store data related to IPFS, you don't actually need a file system. You can do it without a file system, but you can also do it with a file system. And this is left to the user of IPFS Tiny to decide how he wants to implement. And okay, also it is meant to be OS independent, so you can run it bare metal, or you can have RTOS. You can run it on Linux. It's up to you. We like draw the right abstraction layer for the user to complete specific operations that are system dependent, and this makes IPFS Tiny system independent in a way. So basically, if something can run C++, it can run IPFS Tiny. I mean, this is a bold sentence, but yeah, I would wrap it up to this one. So the downsides of everything. There aren't many embedded friendly libraries, like I mentioned before. We decided that we cannot deal with the network stack. We will also have an abstraction layer for communications. So we won't deal with networks and the IP. So this is something we abstracted away. And this is something that led us into inheriting a simplified protocol. So like, we won't use DHTs to route requests from node to node. Everything will be broadcast for this first version at least. And also, we will not solve the problem of incentivization, which means that an IPFS Tiny node will host data whenever you tell it to. It won't look for an incentive to do it. This is something that in IPFS has been sort of solved with Filecoin, but this is something too big to even discuss about integrating into small systems like an STM MCU, for example. So yeah, clearly IPFS Tiny is not IPFS. So how do we connect the two? And this is where Bridge comes into play. A Bridge is basically a node that runs both IPFS Tiny and IPFS. And basically, IPFS can access IPFS Tiny data, and vice versa. IPFS Tiny can access IPFS data. And IPLD makes this very easy due to the self-descriptive data. And this is a draft topology of how this would look like. So you have like a small subnetwork of tiny devices. They are all connected to a bridge, and this bridge merges the data of the tiny subnetwork with the broader IPFS. So let's move into concepts, because this presentation is actually about enabling new concepts. So given that we have IPFS Tiny, what can we do? Let's suppose that we have a distributed ground station network as a bridge layer. So let's imagine that we have ground stations around the Earth that are serving the role of the bridge we described, and they can like talk IPFS Tiny and IPFS. And let's suppose we have a satellite running IPFS Tiny. What we have is something like this. We have a satellite executing orbits, just like before. And whenever it passes over satellites will detect, will actually ask for missing blocks, and the satellite will simply serve them those blocks. Now, all the satellites are connected together. They are all peers with each other, and they slowly assemble the big file that the satellite is transmitting. This could be like a huge experiment file that could be many megabytes or even a gigabyte big. So what happens is that the satellite throws one block at a time over like it is pretty stateless from the aspect of the satellite. The stations simply request blocks, and the satellite provides them. And the ground stations request missing blocks because they can also share blocks with each other, station to station. So basically, the big file is transmitted only once, as any missing block in this pattern will be filled by a ground station, and a second ground station won't actually need to receive the same block from the satellite itself. It can just get it from other ground stations. And on this note, there could be a ground station that is malicious. So like maybe he wants to edit some parts of the data that the satellite is transmitting. So IPLD renders him empty-handed because any slight change would end up in a different file. Like it is trivial with IPLD to detect any file changes. So you can't really edit that. So let's build on top of concept 1. Let's suppose we have a concept same like number 1, but let's add more satellites.
Hey, George, you have 4 minutes left. If you want some time for questions.
Yeah. I will wrap this up like in 1 minute. If you consider many satellites talking with each other as well, let's say it's all in one mission satellites. Satellites can also share blocks with each other. So, for example, one satellite could have downtimes, and other satellites could have those his blocks there. I mean, the satellite's blocks available. So, like you have orbit gossip happening between satellites, and there is cross-satellite block availability. So, the more satellites you have, the more redundant your file storage is, basically. And let's build on top of concept 2. Let's suppose we have even more satellites, and there isn't no specific mission, but instead the IPFS is the mission itself. So you would have something like this. I know it's a pretty weird sketch. Let's suppose that satellites are in orbit, and the only thing they do is store data for the IPFS network. And you could consider this to be like the space layer of IPFS. You would have like the orbit layer, then the bridge layer, which would be the distributed ground stations, and then the distributed ground stations would merge the orbit layer with the Earth layer, basically, with the IPFS that is up and running right now. So this basically makes it interplanetary, so interplanetary on. But it has huge problems, like what is the satellite incentive to store? This is something you have to solve, and you probably can't take a Filecoin into orbit. At least this is my initial take on this. And there is another problem of how do you efficiently route requests and data over this dynamic topology, because you cannot utilize the DHT as the neighbors you can reach at each specific point in your orbit always change. So thank you. You can head to Libre Space Foundation on GitLab. IPFS Tiny is the name of the project. We are open source, of course. Also, some friends from Protocol Labs made this nice domain, arweinterplanetaryet.org, so you can check status of IPFS Tiny there. And we will possibly demonstrate concept number 1, the one with a single satellite, with one of the next batches of cubics, and SatNOGS as the distributed ground station layer.
Nice.
So, thank you.
Thanks, George. We have one question from Milenko. I directly go to it. So is the protocol able to handle large delays, and how does it relate to integrate with DTN BP? DTN, I think, is delay tolerant network /BP. Milenko, you can define what bundle protocol. Thank you. Yeah.
I mean, this is I'm not sure if IPFS Tiny is advanced enough to even address this problem. I mean, everything happens, it's like a block exchange. You do small transmissions of like 1 kilobyte. So I don't understand where delay comes into play here. Perhaps we can discuss this in the lobby.
Yeah, maybe. I think it's in the network. I mean, in the transmission. It is in the transmission.
Yeah.
Okay, any other question? We can take another question for George. Quick one. Else you can reach out to him in the lobby at the break. And thanks a lot, George, and all the best on IPFS Tiny. Keep in touch, because I have also a blockchain project for space. I'd love to integrate that.
Nice.
See you.
Okay. Thank you.
Yeah. All right.
Hey, Red, do you want me? Do you want to make me presenter? You have the presenter
Yeah,
rights.
yeah. We should put you like administrator on that. But I mean, it's okay. Right. Well, next talk is with Freddy Alfredos. So that's for the SatNOGS State of the Union. So we're going to have an update on SatNOGS. That's you. So Freddy, are you here? Are you here? Freddy's an LSF core contributor.
Can you hear me?
Yeah, he's a SatNOGS developer and open source enthusiast. And I remember, I think in 2019, he started his presentation as "I am SatNOGS." So it's going to stay. It's going to stay. So we have to switch to the right one. So, yeah, right. That's your presentation, Freddy?
Yes, yes.
Great. So let me put you presenter. You got it. Don't worry.
Cool.
All right.
So, I'm Alfredo Stamkalis, or Freddy. I'm going to give you the latest updates on the SatNOGS project. For those who don't know, SatNOGS project is a global network of ground stations focused on automating several ground segment operations. So it performs reception of telemetry. It has telecommand and control capabilities in different frequencies. Also, visualize the telemetry and data from satellites. It has a collection of data and other observation artifacts, where artifacts are the results of observations with metadata. We also do orbit determination and TLE generation and satellite identification, and we also record the frequency violations. So all these are done with an open source stack with several software and hardware projects, services, and data. All of them developed, supported, and used from several contributors, from big universities and organizations to individuals. And let's split the projects to three parts: the ground station part, the web and other services part, and operations one. So let's start with the ground station part and the SatNOGS client, which is the software that runs in ground stations. It is responsible to communicate with network and get the scheduled observations and perform them. So in the client, last year, we have some refactoring in the code base, bug fixes and maintenance. We have also improving the artifact supports. We have the new waterfall data artifact, which is in beta phase. We'll talk about it a little later. And we have also configuration for uploading artifacts. So if a station has limited bandwidth, it can choose which artifacts it's going to upload. So in the future, we are going to continue refactoring and improve the artifacts support. Also support streaming for data artifacts, so we can have the data in almost real time. And also we are going to support transmission under the SatNOGS Homes project. Next on the ground station is the GeoSatNOGS and FlowGraphs projects. GeoSatNOGS is the out-of-tree GNU radio module that process, demodulates, or decoding the received signals. And FlowGraphs are the GNU radio flow graphs that are responsible for processing different satellite transmissions. So on these are the supported flow graphs right now for all these modulations. And the last year we have do some improvements in performance and some maintenance work. We have added some new decoders and encoders. We started using SIGMF for metadata generation in order to use them in machine learning and other applications. And we also added UDP IQ Sync that exports data for analysis and demodulation with third-party tools. In the future, we are going to improve and add more flow graphs, do a process on-the-fly flow graph generation. We are aiming to port SatNOGS to GNU Radio 3.10 and flow graphs, and also improve artifacts support and support transmission. The next is the hardware components of a ground station, rotator, antennas, and other hardware-like electronics. Last year, there weren't any significant updates on SatNOGS rotator and antenna designs. However, there were many many contributors in SatNOGS project and in SatNOGS community that have developed, documented, and tested RF components like filters, amplifier, duplexers, etc., rotators, and antennas. In the future, we experiment with new concepts for ground station setups, like the SatNOGS Tiny. There will be a lightning talk, I don't know, today, maybe tomorrow. And we also continue development, document, and testing our ground station components. Let's go now to the web services, web and the other services. First, we start with the SatNOGS network. You can see here the stations. With the green one is the online one, and the orange are the testing ones. The network is responsible for station management, scheduling of satellite observations, and storing, displaying, and rating of artifacts. The last year, we have also here performance improvements and bug fixings and maintenance. We had some also UI improvements. We had changes for supporting artifacts. We also starting support S3 storage for the data and the artifacts. And also we perform almost 2 million observations. In the future, we plan to improve the API and the API client, complete the artifact support, improve scheduling automation, and improve the artifact and observation rating system, and also support transmission here too. Some statistics. We have 255 online stations, 123 testing stations. We perform 5,200 observations per day, and we have almost 28,000 demodulated frames per day. Next is the SatNOGS DB, a crowdsourced database for satellites and satellite missions. And also it's the repository for artifacts. The last year, we had also here some maintenance, performance improvements, and bug fixes. We have added the satellite identifier, which allow us to solve issues we had with NORAD ID. We have improvements of artifact support, and also we have continued the integration of Metasat schema by using JSON-LD format. In the future, we are going to complete the artifact support, improve the API and the API client, improve station and data statistics, and standardize and improve DB service in coordination with other projects that use SatNOGS DB. Next, some stats about the DB. We have almost 800 satellites with 1,300 transmitters, and we have more than 125 million frames from 1,790 stations that are coming from SatNOGS network or they use third-party software for sending their data in DB. We have also the SatNOGS decoders, a service that allows to decode the received frames using scripts generated by kite.io structures. We had the last year new decoders, also satellites, new people from satellite teams involved in the design of their decoders, and also we have decoded the 66% of DB frames. In the future, we are planning to create more decoders, continue to involve people, and also improve the process of decoding. Here are the supported decoders. With blue are the new ones. So the next is the SatNOGS dashboards, a web service that allow us to visualize telemetry and other data from satellite transmissions. We had several satellite teams creating their dashboards the last year, and also use them for daily mission analysis. And in the future, we also plan to create more dashboards and continue to involve more people and satellite teams, and also experiment with some Grafana features with an alerting system when something goes wrong. On the operations side, we have the observation scheduling, which the last year we have improved the auto-scheduler, a third-party software for scheduling observation in SatNOGS network. And also on scheduling, we had scheduled several ARIS contact and SSTV events, observations for these events. And we have observed also more than 15 satellite deployments. And also we have satisfied some public requests from satellite teams to observe their satellite when there was a special event or a special transmission. We are going to continue to automate the scheduling and make it smarter. Also, we are discussing about adding auto scheduling in SatNOGS network, and also we are going to continue to support events and scheduling requests. On the satellites identifications, we continue using SDRF tools and IGNOS for identifying satellites. We have already identified more than 150 satellites until today, and we are building tools that we are going to use the new waterfall artifact, the new waterfall data artifact, for analyzing it and help us to identify satellites. We have also the orbit determination and TLE generation in operations. Also using SDRF tools, we have last year generated more than 140 TLE sets. We usually generate them in the start of a mission when the satellites are deployed, or at the very end, some hours before the re-entry, when we don't have or have few updates of the TLE sets. And also we are building tools for the waterfall data artifact to help us in the orbit determination and TLE set generation. I'm on the last slides, yes. Okay, some highlights and contribution. It's the feedback and support through the issues and community forum and chat. Several contributors also help us to update our SatNOGS wiki, schedule and rate observations, and of course being amazing station owners. For all of these, I want to say a big thank you to the SatNOGS community and all the contributors, and invite you to join us by following these links or contact me in person. Thank you.
Amazing. Thank you, Freddie. I'm like uploading for just 70 people. Freddie, the pipe of activities seems huge. There's a question from Mario. Which will be the SatNOGS features you will dream to implement, but it's not possible at the moment because of whatever reason? budget or not enough resources of some kind. Maybe this person has a magic wand. He wants to help you.
Yeah, I think that yeah, we have many ideas. I mean, what we need currently, it will be very helpful to have more contributors on development and also on the operations, helping us to create all these new features and ideas we have. For example, the ideas for automating the main task is to automate all these tasks that I have already mentioned, which some of them are still in the semi-automatic, semi-manual status.
Semi-Freddy. Okay, gotcha. Yeah, okay. It's interesting. Anyone, do not hesitate to turn on your microphone and speak up your question. There's another one from Dimitri. Clara, you're welcome. Dimitri is saying, are we going to be able to have statistics on types of data processed per ground station? So like ground station X has processed.
Yes. That's something we want to do for many years now, to have more detailed statistics about the stations and the satellites and the data itself. This is a plan, but as I said, if we have more people helping us, we can move forward faster.
Very cool, very cool. I have one question for you, Freddie. So I've seen like the big bump of number of missions, like from 400 to 700, something like this. How can I add a satellite mission in SatNOGS? Imagine somebody here has a satellite mission and they want to add the satellite mission in SatNOGS to get supported by SatNOGS.
Yeah, the current status is to open an issue to the operations repository in the. You can see the link now in the presentation, and you can also we have it in semi-beta testing to suggest your satellite directly in SatNOGS DB. So you can add all the details there and just waiting for a review of your suggestion.
You mean on database.satnogs.org? Yeah.
db.satnogs.org, yes.
Okay, great. Nice, nice. Anyone has another question? I have one, but you first.
I'll be available in the breakout rooms.
Because if you're non-developer, how can you contribute?
Yeah, if the non-developers can contribute with many ways, like helping us to add satellites in database, find information about them, do scheduling or rating the observations we have, or create dashboards, for example. We have many ways for someone who want to contribute.
Very nice. Very nice. Thanks a lot, Freddie. Anyone?
Thank you.
Still have a chance for a question? Else we'll thank Freddie and move on to the next one. Thanks a lot, Freddie. Montos. So next speaker is Arthur. Arthur. He knows how to get himself as a
Yeah, he can put his presentation by his own. Yeah.
So Arthur, so I can present to you Arthur. So because I mean he just started his bachelor. So he has a passion for space and software. So and is combining his dedication to open source space exploration. He founded the Libre Cube initiative that you're going to hear about now some years ago. So that's when you start to get old that you say that. After I studied in Germany and Taiwan, I think that's where you made your first Cubesat, right, Arthur? Almost 10 years from now, he's a spacecraft operators engineer at ESOC, so the European Space Agency Operations Center. And he believes that we should strive for using more space standards for CubeSats in a more elegant way. So he likes to say in a Pythonic way. And I know that Juan is already like that. Yes. So Arthur, thank you very much. let's go and tell us more about Libre Cube, so this open source ecosystem for space and Earth exploration.
Thank you, Red. Thank you, Mantos. So, Libre Cube, open source ecosystem for exploration missions. Libre Cube, librecube.org. That's the website. And there you will see that Libre Cube is built on these 3 pillars that are shown here. So it's open source. So everything we do at Libre Cube is open source, and we only use open source tools. So you need a computer and internet connection, and then you can contribute. We also focus on using free and open standards, space standards mostly, from ECSS and CCSDS, and those are the same standards that are being used by ESA, NASA, JAXA, and also space industry. And we're using those as well. And then the third one is the reference architecture. So what is that? It's basically a menu or like a card where you have these different building blocks, and you can choose the building block that you need, a bit like Lego, and then you build your exploration system. But there's more to the picture. So that would be an overall view of your mission. You have your space and so remote segment. So the machines, satellites, rovers that do your mission operations that you're using to conduct your mission. But in order to control them, you have antennas to interface them, and those stream the data, connect to your operation center. And during this Cubesat conferences, Cubesat workshops, and also this open source Cubesat workshop, we talk a lot about Cubesats, and we talk a lot about antennas, but we don't really talk a lot about this mission operations aspect. Also, Freddie just mentioned it actually, that they need more to focus in this direction, so more support on operations and automations. So this is all under the umbrella of mission operations. I work as a spacecraft operations engineer. I work in such an operations center, so I know that there's a lot of things to do. And in fact, when you run a space mission, most of the time you should spend is on the mission operations and not on the development. So you want to have a long-running mission generating a lot of data, and then making this data available to the users. And you can see here on this diagram, you have these building blocks or these high-level system elements, and they connect to each other via interfaces. For example, let's have a look at this space link. And luckily, this is very well defined in the CCSDS standards and ECSS. So on all the different layers, so for a telecommand chain, so for the commands going up to your satellite, and also for the telemetry, everything that's coming back, you have a fully defined protocol stack. From the bottom, you have the modulation, channel coding, the frames, the packets. It's called space packets. So it's very similar to terrestrial internet, but for space. And on the top level, we focus on the application layer. We focus here on the packet utilization standard from ECSS and on the file delivery protocol. And for most of this, or many of those upper layer stack layers, we have developed already some prototypes. Good. So this would be an interface. But now let's look at this aspect of mission operations center, this element. If we zoom in, we see that it's composed also of a number of building blocks. And so here on this left side, you would have the SLE service that connect to your ground station. These are just the acronyms of the different services. So for the telecommand chain and for the telemetry chain. And these connect directly to your mission control system. Then you have other systems to support this, and you have eventually you want to distribute this data to your users, scientists or consumers. Here we don't really have a standard, to my knowledge, available, but so this has to be defined, and yeah, we're still thinking about what to use, maybe REST or ZeroMQ. But okay, so you have a lot of building blocks, and imagine now the following. That's the nice thing of the beauty of an ecosystem, that if you would start to develop a simulator framework, and this has been defined by ECSS, so there's a standard on how you should construct such a simulator and how you should construct those models that are being run in the simulator. For example, the environment model, so of the space environment, or for your orbit orbit propagation, or for your Cubesat. And imagine the following, that you have this simulator infrastructure that is open source, everyone can use it. Plus you have a model of your Cubesat, which is tailored to your specific mission, but it should be relatively easy for other missions, Cubesat missions, to take your adaptation or your configuration and tune it to their own Cubesats, because Cubesats, they all look very similar, so have very similar properties. 5 minutes already, wow. Yeah, so that would be great, sharing and reducing costs and working all together. So that's the simulator. There's many other building blocks that to work on. Let's have a quick look into the mission control system, how it would look like. This is just a part of it. That would be the incoming of your data as the telemetry chain. And well, you see it, and the frames would be taken out from that. And then finally, the space packets would be taken out from that. And then further down the chain, you would get the parameters from your onboard housekeeping service. So there's, of course, much more to it. But what I want to tell you is that those processing building blocks are defined as Docker containers. So you can spin them up very quickly, and you can make them redundant. So if the machine that runs this data link A service would fall down, then you would use the B service and reconnect to there, and actually you can have it running in hot or cold redundancy. Good. So that's and this we can exercise for all these elements. So we can always zoom in, and we can find out that there's that these things have more building blocks and they have more interfaces. And the goal here is to standardize or agree on mostly those interfaces. The content of the boxes are more or less up to the developers, as long as they fulfill these interfaces and the specifications. And this would be an overall view of a CubeSat system. I'm sure you can fit all the CubeSats that being presented here. They could fit in this scheme. And I think it's important to use also a common naming scheme so that we all know what we're talking about. Let's do a quick overview of the projects that we worked on this year. Well, some of them, so the SLE protocol, I mentioned that's the one to connect to, well, for example, the ESA ground stations or NASA ground stations. We have written a SLE Python API for it, and we tested it. So what we did is we were tracking the cluster satellites. They send over S-band continuously, they send data. And there's a ground station in Taiwan that, so NSPO is the Taiwan Space Agency. They were just, pointing at a satellite and receiving the data, the data stream. And then we connected here with our Python user interface to their machines. So they opened the network for us very, very nicely. And then we could receive the frame information and the data. So this thing totally works. Then some more, link predict. So that we also use to predict the link budget to make sure that we actually can receive a good signal of these satellites. So we utilized this tool. Then another project we worked a bit on, but it's mostly dormant now, is 3D visualization in the browser. Of course, it's using 3GS JavaScript library in the background, but in the foreground, you as a programmer, you can program it in Python. We have written a wrapper for it, so you can use your Pythonic way of coding those 3D visualizations. On the hardware side, this is a bit actually from last year, this project, but still ongoing, and we are refining it a bit. It's basically the onboard CAN bus, so that the onboard computer, central onboard computer, can communicate with all the nodes, power system, communication system, and so on. But the most focus was this year on the CCSDS file delivery protocol. We just heard about the Interplanetary file system. So maybe this is something that we can fit in here, because here this is a protocol which was designed. It's a bit like FTP, but it's made for space application. So, and this protocol makes sure that you get your file from ground to the spacecraft, or the other way around, even if you're traveling at Jupiter and have 40 minutes of a delay in sending that file. So we have done a test here, and this was mostly done in the frame of a Google Summer of Code. Zara, Cheyenne, Siddharth, they were working on this, and they also made a nice GUI for it. So very nice experience here. And for this year, well, for next year, we plan, first of all, to make a bit more regular meetings. You're all invited to that. We coordinate on the chat, so to get the momentum rolling. And yeah, the focus is will be more on the ground segment, because it's purely software development, and we can do this very good from home. But also, if you would like to contribute further to this one-use structure or the power system, which we all have in the pipeline, then you're very welcome to push those projects forward. And yeah, especially if you enjoy working with hardware. Good. So this concludes my talk. I'm happy if you visit librecube.org and join the chat, and I'm happy to answer your questions if you have any. Red, I cannot hear you. Now you're double muted. Oh, is it possible to integrate SatNOGS or R2 Cloud?
Yeah.
Theoretically, this should be all possible, because at some point in this overall schematic, there's an interface to a ground station and also to a database. So if this interface does not support it yet, then well, it's up to you potentially to create an interface for it.
Yeah, back.
Yes, Red, we're back.
Yeah, you can hear me. All right. Cool. Arthur.
Yes.
I have a question for you. How do you feel the engagement and the reaction to the project? So, because I feel like you're an engine, a driver for most of the applications, and how do you see that? Growing up. Yeah. Tell me.
That's actually. I always find this, for example, the Python project or the Linux project. I always find it amazing how they make these things work to coordinate a large audience and a lot of contributors, but still follow a common path. Yeah, I still find this not so easy. So we have a bit of fluctuation here because people join over these opportunities like Google Summer of Code. But the question is how to keep them engaged further. Yeah. So maybe this also leads to the question of bounties. Yeah. So would it be feasible to offer them some financial support? We try to do this during various opportunities, but mostly I'm looking also forward to voluntarily contributors. And in return, we're working on technology that maybe sounds a bit profane if I talk about file delivery, Doesn't sound like too exciting, but this is
This
at
is part of the
ESA, for
backbone,
example,
right?
this is like the future of how ESA is going to operate the satellites, file-based operations. So if you have this in your CV, I think that's a good asset already.
Yeah, yeah, it's good. I mean, that's good to sell the CV. That's good. Thibaut, I see you're typing. Oh, Mona.
Yes, I was writing it just to say, Arthur, we are like, I'm going to see in my team, we're super interested in this kind of development. And I'm going to like stay in touch with you to see how we can collaborate or do something together, because it's, I see the future of what we're doing. So I'm super interested.
Very nice. Regular meeting from Thibaut from Isae, France. Good. Mona Abd El Salam. You have a question? You can take the microphone if you want. Turn on the microphone. I don't think I see her anymore. Okay, disconnected maybe.
Maybe this one was more like a bye-bye.
Yeah. Thanks, Arthur. Okay, all right.
Okay.
So, any last recommendation for anyone out there on the how to contribute or anything?
Yeah, tomorrow we are going to have also the discussion on the mission control systems.
Yeah.
In the afternoon, and I'm going to present a number of projects like OpenMCT and some open source mission control systems. And I would be happy to hear about people who have worked with those projects, about the experience, and to discuss also some shortcomings. And well, if we will start how we can fiddle this all together and make it work.
Yeah, and see where are the missing pieces where we need contribution maybe. And yeah, nice. Thanks, Arthur. We have no more questions here. And this is the end of session 2. Thanks a lot, everybody. So we're having a break with the breakout rooms. Thank you, Arthur. So on room 1, you will have astrometry, where yeah, this is it. Astrometry with Boris. Room 2, IPFS Tiny. Room 3, SatNOGS, the State of the Union with Freddy. And on room 4 with Arthur on Libre Cube, so you can continue the discussion during the break. And we are back in 20 minutes. So feel free to join those rooms, or stay here if you want to chat, or join room 5 for the lounge, because here we might be doing some work. So okay, thanks for the breakout rooms. They're here. 1, 2, 3, 4, 5.
Bye, people. See you in the next
Andrew is in room 4 already. Room 2, George and Amon. Anton is room 5. Jan Peter. I think Boris is out of the audio. I will put his link over there. BM. Are you okay, Mantos?
Yeah, everything's good. Are you okay?
Yeah. It's quite difficult to join. Oh, Boris is in the room. Let's check if he has a connection.
So we're almost ready to start with our next session here. And I can
Yeah, let me
Andrew.
upload those presentations. And seems like we're missing talk number 3, the power system.
I think it should be on your...
I sent it in around 30, 40 minutes ago. I can send it again if you need it.
Okay, I have it. Thank you.
Cool. So I think we are right on time and we can start. This next session is going to be heavily around Orsat, which I think is long time overdue for open source Cubesat workshop. Since you've been doing great stuff for years now, and finally it's time to present them in depth on various different talks that we have today. And thank you to all the Orsat team for being supportive and also submitting all those talks. And I think it's going to be a great session. So for our first talk, we have Andrew. And Andrew is adjunct faculty to the Electrical and Computer Engineering at Portland State University in Portland, Oregon. And although his day job is in medical devices, his hobby is teaching and helping the Portland State Aerospace Society, an interdisciplinary student team of space hipsters who build amateur rockets and CubeSats. And for this first talk, let's go and come find out why building your own open source modular 1U to 3U CubeSat system at the university is a terrible and costly idea that might actually work out in the end. So, Andrew, over to
Thanks,
you.
everyone. We are super, super pleased to be here. And Pierre, you're right. We should have been here years ago, but we were too busy staring at our own navels, building our own system. So I'm going to just tear through these slides. I'm sorry, it's going to be a huge overview, and hopefully this will give you the context for the talks that follow that will have more technical detail and will be presented by the students. So a quick background for us. We are a student group in Portland, Oregon. We are interdisciplinary, so we're mechanical, electrical, computer science, and a bunch of non-engineering students. We've got business people and physics and psychology even. It's pretty neat. And the idea is that we kind of simulate a space program. We've got all the different things, including finances and blah, blah, blah. We're completely open source. Everything we've ever done has been published now on Git. And we are crowdfunded mostly, although we do get some funds from the Oregon Space Grant Consortium. And we have no idea what we're doing, so that everything we're presenting to you right now is complete vaporware. You should not believe any of it. You should take it with a giant grain of salt, which is what we say in English, I guess, for when you shouldn't believe it. But it's there. And we look forward to getting some feedback for you. So we started with rocketry. On the right, you see one of our amateur rockets, and just to the middle right, you see an amateur radio, amateur rocket avionics system that we developed. And we suddenly realized that, in fact, what we'd done is we developed a CubeSat that was cylindrical. So we applied to the CubeSat Launch Initiative, which is a NASA initiative. It's like the QB50, right? And got in, shockingly. And so we started building a CubeSat. And as we were building a CubeSat, we realized that we were building something a little bit bigger than just one mission. And the reason for this was we looked around because we didn't really want to design our own kit. We wanted to buy it, or at least get an open source kit and build it ourselves. And all of you teams that are looking at CubeSats is the same thing, right? It's $35K for a 1U, or up to $125K for a 3U with ADCS. And so we just couldn't afford it, right? But doing it yourself is stupid, right? You guys know this. These things are damn complicated. We can hardly put together, as my team, one open source software project, let alone a huge interdisciplinary hardware software system. And it's still going to cost you in the long run more than you'd like. So we looked around and we kind of put together a requirements list of what we really wanted, and it just really didn't exist. We wanted a scalable design. We wanted independent subsystems. We wanted it open source. We wanted scalable from microcontrollers to Linux boxes, and it really had to be student team friendly, meaning we could give chunks of the project to a student team. They could build a board, it could catch fire, we could fail them so they come back next year, and then the ones that do work we could put in the satellite and we could hot swap them and all that kind of stuff, and of course based on standards. So we thought, what could possibly go wrong? Let's do it ourselves. This is not a good idea, and I don't recommend it. We've been working on this, and we've known Pieros in Libre Cube and in Libre Space for a long, long time, but we've not really participated because we've been too damn busy building this system. And we spent hugely more money on building the system than we would have originally. So it's not a good idea, but we wanted it and we thought we were uniquely suited to do it. So we did it. So I'm just going to go over an overview. So the Orsat system is a card cage system. It is, in fact, a Cubesat developer specification Rev 13 and 14 compliant Cubesat system. You can see here that we have a full CAD model of it, and this is one of the early prototypes of it. These cards slide in and out to a backplane. And why a card cage? And the answer is it's excellent for student teams because you can give cards to the kids and they can plug it in and they can catch fire and we can take it out and put another one in. And it's got a common API, right? A mechanical, electrical, and even software API that we can give a student team. And that's really important. And so when we were designing this, we thought, okay, we've got to make it hot swappable for the students. And we wanted something that wasn't a toy, right? It's really easy to make an educational project that's more Arduino than Linux box, right? And so we really wanted to make it dense and ready for future missions. So it's the way that we've done it. It's got about 40% more usable board area than a PC-104 stack. And there's about 8 of these cards, we call them per slot. There's a problem though, which is that when you do these card cages, it's really difficult to go up and down through the card cage. So Z-axis traveling is hard, except on the backplane. So we do have a scalable system. We've got a 1U CubeSat handed off right now. We have a 2U Cube, 1.5U CubeSat actually in design, a 2U CubeSat in design, and a couple other student teams around the world are building a 3U version of Orsat, which is very exciting. Just some nomenclature. So these are the frames that we have. These are the cards we've talked about. The cards on the top and the bottom are special. And then there's caps that kind of fit the top and bottom on the Z-axis. And then, of course, the solar modules go around the sides. The structure itself is anodized aluminum, and it's machinable by students on a router, kind of. It's a little more complicated than it should be, but the mechanical teams will talk about that. We come up with these little kits. So there's a kit that you could put together a satellite with. And there's this really neat thing that the mechanical engineers will talk about, which is we get to clamp those cards in for vibration and thermal reasons. I talked about this. Luckily enough, it's not that expensive to have made for you. If you go to hubs.com and you get one made, it's about $1,200. Although if you get 10 made, it's $400. So it's really, really, really cheap if you make them in bulk, which is what we're trying to do. I'm going to skip over this and let the MEs talk about this. So what's in the bus, right? So exactly what you'd expect from a small CubeSat. It's got a 2S1P, well, actually 2S2P kind of lithium-ion battery pack that's directly connected to the bus, so it's 7.2 volts. And we have this power control where we can power each of the different cards called the Orsat power domain. And then we've used CAN, of course, right? So we've got 2 independent CAN buses right now that they're shorted together, but in the future we'll have 2, and then a shutdown circuit for the whole thing. Over here, you can see the main connectors here with all that stuff on it. And then we've got an area here for radio frequency connectors. We use SMPMs. And then over here, we've got an auxiliary port, and that's for Ethernet or whatever else you'd like between cards. One of the things that we really realized is that every single mission is bespoke, right? You need a system that you can use, but every system is different. We're thankful to Osh Park. You may have heard of them. They're an open source hardware park. I don't know what park stands for. And they support a lot of open hardware projects. And so they're supporting us. We use their 2-layer process for the simple boards and 4-layer boards for the more complicated and the RFE ones. And they've really helped us out. So in the satellite, we have 3 layers of computing that we'll talk more about in the firmware talk. We have a Cortex M0 based on a STM32F091, and that runs ChibiOS, which is a real open source real-time operating system, and CanOpenNode, which is CanOpen, of course. And so that's the distributed thing that runs on batteries and solar panels. Then we have an onboard computer, or OBC, that we call the C3, Command, Communication, and Control. That OBC runs a Cortex M4F that also runs ChibiOS and CanOpenNode. And finally, we have what we call mission processors, which are Linux boxes on a single chip. Basically, if you know the BeagleBone, this is a Pocket Beagle chip. It's an Octavo OSD 335X-SM, and that's basically a TI Cetera processor with built-in RAM, and that runs Debian Linux. So one of the things that was really important to us is that we can onboard people really fast, because students are terrible at this. They don't know anything, so you have to bring them all up. So you can start with an $11 COTS development board from DigiKey or wherever. Then we can give you a little prototype board where you can solder and do stuff. And this is an actual card that fits in the satellite. And then finally, you can graduate to an actual card that it has the application thing and has been built professionally and all that kind of stuff. But usually, we're building stuffing these ourselves. There's also two levels of software tools. So if you're working on a Linux box, you buy a Pocket Beagle, and that's your development kit. And then this is the same chip here is here, and then this is our star tracker. That's again theoretically built professionally. So far, we always said we were going to have our satellites built professionally, but the one we just handed off was totally stuffed by students. So it was just luck. Each card. You can see here in the stack, you can see these little white FFC, flat flexible cable connectors. Those guys are how we debug each card. It's common. There's JTAG, a serial port, and for the Linux boxes, host and device USB, so we can talk to them as an Ethernet port. And there's this common debug board that you can plug in USB cables and all that, and that's shared between cards, which is really nice. This is our flat sat. So we needed a really accessible flat sat debug integration tool. So you can see here, this is our backplane. It's literally a ribbon cable between little cards that the cards plug into. So battery pack, inertial measurement unit, star tracker, OBC, etc. That way we can probe us up. So everything's based on CAN. We use CanOpen, in particular CanOpenNode, which is an open source library. If you don't know it, CanOpen has its problems, and we are deep in them, but it works, which is great. So just to quickly run through some of the subsystems that we currently have, and I'm running out of time, so I'm going to blow through these. We have a solar module that's talked about more in an upcoming talk, but they're Spectralab gallium arsenide cells. It can be redone for silicon, and we hope to do that just to reduce costs for other people one of these days. We're super proud of these because it's a true maximum power point tracker on each independent module, and it's not just a controller, or it's not just a battery. Nope, it's really an MPPT that's software driven, so you can actually work on the algorithm if you want and switch algorithms. The battery pack is exactly what you'd imagine. It's an 18650 cells. It's 7.2 volts at 5.2 amp hours. You can fit about one battery card per U. So 1U has one battery pack, 2U could have 2, and 3U could even have 3 battery packs if you wanted. Although now you're pushing some of the 100 watt hour limits, especially for ISS deploy. It's got everything you'd expect: fuel gauge, cell balancing, all the things, and a heater, of course. A heater because PRS told us to put a heater in. So the C3 is exactly what you'd expect. It's the STM32 with ChibiOS. It's got an L-band receiver at 1.26 gigahertz and a UHF transceiver up and down. And that way we can do full duplex. The only radiation tolerant thing on any of this is this one little comparator chip from TI, and that is our watchdog circuit that power cycles the entire satellite. When it goes off, the whole satellite shuts down. There's some FRAM and RTC, and then we've got 16 gigs of storage to just hold on. We have a cute little tri-band deployable turnstile antenna. So you can see here, this guy right there is the stowed antenna, and this is it after deployed. Standard tape measure antennas at UHF, L-band, and also L1, our GPS antenna. And it's RHCP, right-hand circularly polarized, and omnidirectional. So this is an example of one of our star trackers. We use a on-semi either black and white or color CMOS sensor. We're flying a color because we want Earth images, not just star tracking. It runs Open Star Tracker, which is this amazing open source project that we are excited to fly. We've written our own kernel driver for something called the, programmable real-time unit that runs on the Satera that interfaces with the camera. And of course, CanOpenNode and Python and running on Debian Bullseye. Our GPS is similar. It uses a commercial off-the-shelf Venus GPS receiver that's been got special firmware for space, as well as SDR GPS receiver, the MAX 2771, which is not functional right now, but it's up there. And so we hope to finish that using GNSS SDR, and again, CanOpenNode, Python, Bullseye. And you all know we need a ground station, right? So we're extremely happy about SatNOGS. Thank you, SatNOGS people, because we would be dead without you. And we need SatNOGS comms now, right now. And so we didn't wait. We made our own thing, and we played off SatNOGS, and we hope one day to play directly with SatNOGS. And we call it Uniclogs, the University Class Open Ground Station. Sorry for the name. They're expensive. They're like 10K each, but fully SDR, transmit enabled, good antennas, commercial antennas. And we've got one that's being built in the UK right now, and we've got two here in Portland, and we hope to have more around the world that we can start sharing communication, transmit capabilities, and of course regulatory compliance. Right? We don't know what that means yet. So just to wrap up, we have 3 missions right now. Oregon, the state of Oregon's first satellite was just handed off last week. It's on Transporter 3. That's coming up no earlier than January 10th. Thank you to Spaceflight Industries that gave us the free ride, which is amazing. And that was fun to integrate up in Seattle last week. So that's where we're going. It's an ISI deployer on the Sherpa orbital transfer vehicle, which is called Sherpa LTC-1. We're now building Orsat 0.5 because, for reasons, we called it this. And this is a 1.5U bus, again, for reasons that we didn't expect. And this is going to be a test of our attitude determination control system, which will most likely catch fire in space as opposed to actually work. But we're going to test it because after this, we finally get back to the original Orsat project that was a Cubesat Launch Initiative project that from back in 2017. And that's for a handoff in late 2022. So late next year, about a year from now, we'll be handing this off. And this has got the full ADCS and shortwave infrared cameras and a bunch of other missions. So thank you. Please contact us. We are coming out of the woodwork now, or the closet, or whatever you want to call it, and happy to start working with our peers, and super happy to find out about Libre Cube and who are going to solve all of our CCSDS FDP problems for us. Thank you, Arthur. And anyway, so questions?
Thank you, Andrew. That was super awesome to see, and the progress and how far you've come, and congratulations on your delivery last week. That's a huge milestone, I can imagine. So there are already a few questions here. So, for example, for CanOpenNode, that it has no profiles for motors, for O2 motor support. Like, did you have to add this one, or?
Yeah, so we're bad at CanOpen. And so we didn't bother with the sort of device profiles, I think they're called, for motors or for this and that. We just used our own PDOs and SDOs and things like that for each thing. So yeah, we didn't bother.
Okay. There's another question about if you can elaborate a bit about the selection of the backplane connectors.
Oh yeah, we went through a lot. I'd encourage people to contact us offline at orsat@orsat.org, and we have a lot of documentation about why we chose these things. We chose these things because they were high density, 1.27 millimeter connectors. They've got great sockets and pins. They have 3 connectors each, so they're super reliable even through vibration. And we want to run these on rockets, so we care a little bit more about vibration than most. And they're super high density, and they've got great, one of the worst things you can do is give an electrical engineering student something that's precise and mechanical, right? and so it's got a lot of robustness and a lot of angular and displacement misalignment, which works well. Same thing with the SMPM connectors. There's a barrel that goes between them, so they can have like up to 0.5 millimeter of misalignment, and they still break, which is great. So all of those backplane connectors were very, very, very carefully chosen, and we actually went through like 3 or 4 revisions.
Cool. There's a more general question regarding the cost of a 1U CubeSat and the ground station, which I suppose it depends on what you're going to put inside of it, right? But
we come up with we say for a 1U CubeSat, you could build an Orsat for $5,000 or less. And we think you could be aggressively less, like $2,000 or $3,000 if you did it right. But I wouldn't recommend it, so it's more like 5,000. But you always need to build at least 2 or 3. You can't just build 1, right? And so that means you're really going to end up spending, I'm going to say, about $7,500 for a small fleet. We do everything in 3s because we get 3 circuit boards from Osh Park. So we build engineering unit, flight unit, and a Destructo backup parts unit. And the ground station's like 10K. It's expensive, maybe even 15K. So you're talking about a minimal investment for an entire system of probably 20 to 25K US dollars.
Cool. That's
cool.
Still.
I also have a couple of questions, but they're very specific, and maybe they will be handled in the next presentation. But how about testing?
Testing? What's that?
Like, did you put it in a vacuum chamber and a vibration? Yeah.
Yeah, I'm sorry. We didn't have time to talk about that, and I should get off and let the other folks talk. But yes, we have a local, very janky TVAC chamber, and we have a local vibration table that we use, and then of course the real testing is the integration testing for software, right? That's the really big deal. So we have that was flat side. I guess I talked about that, and we'll talk more about that.
Thanks.
Thank you.
And I think that we have some time for a final question, which is a more broader one. What do you wish you knew now back when you started?
Everything. I think that for those of you who've gone through a CubeSat before, you realize that everything's super, super terrible. Everything is hard. Everything's a trade-off. And that's part of the fun, really. That's why we like these things, because it's an exercise in system engineering. But I think I would have liked for someone, like, really, hats off to UPSat for being the first one and for sharing everything with us. I wish there were more projects that we could look at and like that and see. So I wish we did more research when we started, rather than just kind of cavalierly, blindingly started off on our own thing. We've learned a lot, and this kind of thing would have been great, 5 years ago when we started, had we looked around. So.
Well, we look the torch and you carrying it with such grace and sharing again everything that you can. So thank you for following up on this trend and actually being so much committed on open sourcing and documenting in such detail your project. It's really remarkable to see. And with that, I think we can move on to our first more in-depth presentation, right? From Orsat team, I'd like to invite Marvin. Thank you, Andrew, once again. And Marvin, yep, we can see you and probably hear you too.
I think so.
Yeah, great. So welcome, Marvin. And Marvin is a high school senior and mechanical engineer working at the Portland State Aerospace Society on the thermal and mechanical design of the Sirius Flux, I hope I'm pronouncing it well, camera mission. Orsat structure, also the frames, and preparing the 1U CubeSat for flight. And we also have Hayden with us, so welcome, Hayden. He's a senior mechanical engineer student who has been working with the Portland State Aerospace Society on projects such as the deployable turnstile antenna, the mechanical design and manufacture of the reaction wheels, and building for flight for our the first 1U CubeSat that you delivered. So now we're going to be hearing more in detail about the mechanical design and mechanical architecture of Orsat. So take it away, guys.
All right, thank you. So yeah, today we're here to go a bit more in depth about the mechanical side of things than what Andrew had talked about. So let's just jump straight into it. So like Andrew had mentioned, Orsat uses a card cage design, and there's a few features that come with this. So the first is that we've implemented a card wedge clamp design, which really helps us ensure structural rigidity throughout launch. And that helps with vibration. That also helps with some thermal properties that we'll talk about later. It's also designed with modularity in mind. So like Andrew had talked about, each student can have their own independent card, so they can work on their own independent mission and their own independent subsystem as a part of this Cubesat. Furthermore, the Orsat design also has a 40% greater packing density than the traditional PC104 Cubesat stack. So that's really one of the really important features that we have on our Cubesat architecture. As you can see here on the left and the right, we have a few screenshots of the CAD or computer-aided design of our Cubesat. So on the left, you can see an assembled view with everything put together, including fasteners. And then on the right, you can see an exploded view.
So as Andrew had mentioned, everything is meant to be very scalable. And so, a lot of the systems really look kind of the same between the 1U, 2U, and 3U. You can see that we're even reusing the solar panels and stuff like that. And it's all the same cards that can fit into everything. And so it's the same kind of mechanical clamping mechanism that is used across this whole kind of scalable 1 to 3U system. And it really allows you to have a lot of flexibility with your missions and still kind of, fill all your requirements and stuff. And so specifically talking about kind of the construction of it, it's really easy theoretically to make. You can just make all of the frames, they're a flat plate, and so you can get that made out of a 1/2-inch thick or 15mm stock, just aluminum plate. Theoretically, all machinable on a 3-axis CNC, hopefully by students. That's the whole kind of goal of our project. And so that's able to make it really low cost, which is really nice, as well as we try to use standardized just COTS fasteners. We try to use as many like M2s as possible just to simplify kind of the whole kit of it. You can see there on the right there, the 1U structure kit. That's kind of all of our fasteners and tools and everything that we need to put the whole kind of flight unit together. And so it is very helpful not having to sort through like, a billion different screws. And so standardization really helps both with cost and ease of manufacturability. And that kind of all comes together, obviously, in cost. And so, for like, obviously, economies of scale come into play here. If you're buying maybe like 2 sets of the frames, it's around $1,200. But if you really start to like, have a significant investment, you can get it down to about $400 per piece, which is really nice.
And of course, all of our manufacturing drawings that you will need to machine the frames are all available in open source on our GitHub page, and they're all completed according to the ASME-Y 14.5 standards. So those are all ready to be machined by any machinist in the US or internationally. So talking a bit more about the built-in card clamp. So the card clamp design is really intended to help us fully compress this card that we have onto a top ledge that we have on the frame, as you can see circled in red. And what this allows us to do is really provide some structural rigidity to our system that we wouldn't usually get with a card wedge or a card case system. It also provides us with several thermal properties that are really essential to our architecture. So this entire architecture is designed to be thermally but not electrically conductive. So you can see on the left-hand side, on the edges of each of the cards, there is a copper ground plane here. And this allows us to essentially thermally connect each of the cards to the frames. All the frames are anodized with type 2 anodization in black, which allows us to keep this thermal transfer between the card and the frame so we can dump heat without establishing a ground connection, electrical ground.
So there are parts of the satellite that we do want to have a ground connection now. And so to start that off, those 4 little bosses there you see circled in red are all kind of the frame connection points between each of the 4, plus X and minus X, and then the 2 Y sides of the frames. And those are all non-anodized, so that way it is electrically conductive between those 4 sides. So you have this whole unit that's completely electrically conductive to itself, and then everything on that is anodized aside from a few specific connection points, specifically for the backplane. So you can have an electrical ground connection there, as well as you can specifically request, as in that top large circle there, you can specifically request any of the top cards registers to be unanodized. That's specifically for our turnstile mission. So, for any kind of like RF type grounding and stuff like that, it provides a lot of versatility.
So talking a bit about some of the really key subsystems of Orsat, we have our battery card, which of course we need on every single CubeSat that we design. So there were a few considerations that we had to keep in mind when designing the battery card. So first off, we wanted it to support at least 3 independent inhibits, which we used for, in order to meet the NAORAX or International Space Station deployment specifications. And we also wanted to ensure that it was thermally isolated from the structure, since the batteries do need to be above 0 degrees Celsius in order to operate optimally. So to resolve these problems that we ran into, we, instead of using the inhibits that we traditionally see on the z-axis of the CubeSat, we have 4 rail-based inhibits that protrude from the -x and the +x frames of the CubeSat in order to meet 4 independent inhibits for each of the battery packs. And we also have a non-thermally conductive contacts on the edge of the card. So instead of having that copper ground plane accessible, we just have the very basic fiberglass. Another one of the really important missions that we have on Orsat, specifically our 2017 CSLI mission, Orsat-1, is the Cirrus Flux camera. And this is an especially important system to consider because of the way that it's designed. So it is incredibly heavy, around 1 kilogram in mass, due to the thermal masses. The copper thermal masses are incredibly heavy and make this an incredibly difficult subsystem to work with. And they also need to be thermally isolated from the structure because of the high thermal load from the shortwave infrared sensor that we have. And also because of the sensitivity of the sensor, we do want to keep it very, very cool. So I think around -5 degrees Celsius or around -8 degrees Celsius. And in order to resolve those problems, we ended up implementing fiberglass brackets, which allow us to mechanically mount this very heavy piece of mass onto the frame. So you can see there's quite a bit of versatility with their design, which allows us to increase the amount of mounting points for increased rigidity for incredibly heavy systems like this. And we also isolated the copper thermal masses from the conductive aluminum frames, which allow us to, once again, get that thermal isolation.
So obviously, if you want a satellite and optical payloads, you will probably want to be able to point the satellite. And so that's kind of where our reaction wheels and ADCS systems come into play. Similarly, with all things Orsat that you've seen so far, we try to make it very easily manufacturable, very, low cost. And so that was definitely a challenge with this. But as you can see in that top right there, you can fully machine kind of all the weird complex geometry that comes about with the tetrahedral reaction wheel design on a 3-axis. Being able to drill those holes is another story that is, theoretically doable on a 3-axis machine, but you will need some kind of bracketing and stuff like that. But the point being is that it is actually a very low-cost design. We've had a few designs in the past that required like 5-axis milling, and this really brings down the cost, which was a really fun development to work on. A big thing is that it had to be space efficient, obviously, as you've kind of seen with all of our, incredible packing density. And so kind of going through the design considerations of it, since it's a kind of an active system, we thought that having it on a card would cause a lot of like undue vibration that we didn't want to deal with. And so kind of the flexibility of our system allows us to just, get rid of the card system for this and just bolt it directly into the frames. You can see that those 5 fasteners there are able to rigidly mount it to the frames. And so to keeping with that, very space-efficient system, we have open air Z-axis as well as solenoid magnetorquers kind of occupying that space in between the tetrahedral reaction wheels. And talking about the solar panels, Andrew kind of talked about the electrical part of it just briefly. Specifically, the thermal part is pretty interesting. You can see there on the left those kind of copper traces around the outside of the card, and then even in the middle there, that specifically matches up with that kind of orthogrid pattern on the frames on the right there. And that's so that way they can be thermally conductive to the frames, and it's actually able to offload a lot of the heat load that comes on from being exposed to the sun all day. And so that allows the solar panels to keep at a cooler temperature and operate at a more efficient voltage. And then our star tracker, of course, is kind of the passive component of our ADCS system. It is pointed out the +x of the CubeSat, as Andrew had mentioned, kind of cutting through the z-axis is not exactly optimal for cards. And so it's really nice to be able to have this whole thing fit within a card and actually not take up like an exorbitant amount of space. And so it is nice to kind of prove that you can still have a complex system that's even an optical payload without like cutting through multiple cards all at once.
So just talking a bit about some of the tools that we use in order to optimize our workflow. We use SolidWorks in order to do all our mechanical designs, including CAD manufacturing drawings. In order to version all of our designs, we utilize a tool called Git, which is an open source distributed version control system. And we use that to version control all of our CAD designs, all of our files, all of our drawings, just so that we're able to go back in case anything goes wrong, any of our designs don't necessarily work. We can always go back to an older revision. And with that, we also push all of our designs to GitHub. So all of our designs are pushed to GitHub for public release and also for storage for our own use. So all of our files, all of our source files are all accessible on GitHub if you're interested.
So you can see that that top right picture is actually a picture from our recent test campaign for our Flight 1U Cubesat. And so I think someone was asking about that earlier. And so we were able to vibration test it to the specifications of the Falcon 9 launch. It was kind of exciting actually because for our vibration test, we didn't have to use Loctite, and we simply just torqued down the screws, and we had nothing came loose, and we were able to go back afterwards, and everything was still like pretty much torqued to the same specification, which is really nice. It really kind of shows the robustness of our system. And so although this is easy for a 1U, maybe a 2U will be another story, because that'll be a lot more fasteners to screw in. And so as I just talked about, that was our test campaign, and this is our flight unit for Orsat 0. It is our first satellite in our state of Oregon here in the United States. We just handed off that last Friday. It'll be launched up in early net of January 10th in 2022. And so it's super exciting. Again, thank you to Spaceflight. And so Orsat 0 was kind of our baseline kind of critical subsystems, the battery, the onboard computer, and then GPS antennas, and then our passive like star tracker component. And so Orsat 0.5 is kind of aiming to first introduce our active component of the ADCS, the reaction wheels and magnetorquers, before we go on to our next mission, which is Orsat 1.
And looking a bit further into the future, we have Orsat 1, which is the project that really started it all. So that was our 2017 CSLI program. And this is scheduled to hand off around 2022 with deployment in 2023. And what's really important about this payload is that this includes every single system that we've been working on. So this includes Orsat Live, and this includes the incredibly, incredibly heavy Cirrus Flux camera. And this is really a test of everything. And hopefully all of our previous missions, Orsat 0 and 0.5, all provide the flight heritage we need in order to have a successful CSLI mission. So yeah, thank you so much for listening. All additional information can be found on orsat.org, and all of our CAD files and source files can be found on our GitHub.
If you have any questions, feel free to send some to our emails. Thanks for your time.
Thank you, Hayden and Marvin. I think that we have time, for a couple of questions here, and I can see some quick ones. There's one about the mass of the structural part itself, like the 1U version of it.
The 1U is about 1.2 kilograms, so it is underneath the specification, but very close. Kind of interesting, Marvin had talked about the Cirrus Flux camera, about how heavy that is. That's about 25% of our 2U mass. So our 2U comes in about 4 kilograms, which is interesting.
And I think the question was also about the mass of only the mechanical part, so without the slots and without the cards and anything else. Just the design of the mechanical.
That's a good question. I don't know if we weighed that. Yeah.
So off the top of my head, I don't remember exactly, but I think it comes in for a 1U structure probably around 600 grams. I'm not exactly sure off the top of my head, but if you are interested, all of our source files are on GitHub, and you can go ahead and mask them yourselves.
And if I can jump in and say a quick thing. This is a battle tank, and so there's a lot of optimization here to take weight off if you want to. We don't need to. We were under 1.333 kilograms, so screw it, we're great. But if you need to, you can.
Is it possible to 3D print it? Did you do that before?
Yes, definitely. So it is definitely possible to 3D print. We've used SLS to 3D print this for testing purposes. We have our 1.5U and 2U version of this structure 3D printed and tested. We are looking to print a 3U version too, but 3D printing definitely works.
Okay. Was great, amazing talk, and I have to bring up this question. Sorry, because you mentioned that you were using SolidWorks, and there's already one problem for me because I don't have it, but I would like to look into your design. So I was just wondering, why did you consider using, for example, FreeCAD before, or was there a specific reason that you went for SolidWorks?
Yeah, definitely. So for us, SolidWorks was just the easy option because we were sponsored by SolidWorks and it's really an easy tool for us to use. We haven't really considered using FreeCAD or anything of that sort, but I believe we have considered just uploading the files in just a very basic step format so you're able to access using SolidWorks.
Because it happened to me as well, this trap as a student. I had licenses for MATLAB, for Altium, blah, 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 blah. But once you graduate, then you realize, oops, I'm not student anymore, and I actually have to pay those big license fees.
So this is actually an important point, Artur. So I'll just jump in. Sorry, Marvin and Hayden. Yeah, we cringe every time we boot SolidWorks on a Windows platform, and FreeCAD just isn't ready for us as students. And SolidWorks is supported in education, and we're moving more and more towards Onshape, which is a cloud provider that's cross-platform. And so we'll probably do that specifically to support Linux and Mac OS. But in one day, we look forward to moving to FreeCAD, just as we've moved from EagleCAD to KeyCAD in the last year. We'll probably start moving to more free and open source tools, but not right now.
Okay.
Good. One last question. Sorry to interrupt. You mentioned Git, and it just makes me wonder because you're talking about step files and design files, binary files. So I assume you must have, how do you manage? Write very detailed commit messages, or how do you know what commit was what?
Yeah, so we do definitely have to write pretty detailed commit messages for everything. And like you said, with binary files, it does become a bit harder to deal with. Our Git repositories are gigantic, I think around 10 gigabytes for our mechanical repository. So it's hard to deal with, but it's what we kind of have to use in order to version our design files. But yeah, very long commit messages just to know what we're doing.
As we've kind of gotten more matured with the system, there's been less merge conflicts, but you know, there's always a fun merge conflict to deal with.
Thanks.
Yeah, thank you guys. Is there any other questions or?
I think we are on time right now, so and I don't see any other questions here. So yeah, I'd like to thank you again, both Marvin and Hayden, for the introduction to the mechanical aspects of Orsat, and invite our next speaker, which should be David. And do we have David?
Hi, yeah, I'm here. Sorry, I'm there we go. Webcam.
Hey, we can hear you and see you, so welcome. So David is an undergraduate electrical engineering student at the Portland State University in Oregon. And at Portland State, he has been a core member of the electronics team with Orsat and working on the milliwatt scale power electronics and embedded hardware systems. He's going to give us an overview of the electrical power system. So David, if you're ready, take it away.
Great, thank you. So yeah, just kind of to take it back real quick to what Andrew had said earlier, a lot of the requirements that were influencing the power, the design of the power system specifically, is we wanted scalable design. It had to all be cheap. It had to be open source, obviously, and it had to work specifically in a student learning environment, which has a lot of unique system engineering problems. So kind of how we took those requirements and how that influenced the design philosophy of what we were working with is we decided the best way to create something for the educational space was to provide a series of proven design modules that had been tested and we knew they worked and were reliable. And for the power systems, what those modules look like is we have a battery card, we have a solar module, and then we also have something called the Orsat power domain, which we'll talk a little bit more about later. what this leads to is it's a bit more of a distributed electrical power system. It's not like we have a card that is the electrical power card that does all the voltage regulation, the batteries and the power point tracking and all that. It's kind of all over the place. It's distributed among multiple systems. And this is good because it gives us a lot of modularity and a lot of flexibility in how we actually configure an Orsat. But one of the problems with that is it leads to a lot more of a complex system architecture, which can be a lot harder to understand at a system design level. And then Andrew had touched on this, but when we're looking at our backplane just from a power perspective, it's pretty boring. There isn't a whole lot actually going on the backplane. The power that we route through it is the actual battery voltage itself, so 7.2 nominal. We have the Orsat power domain. The data connections that are traveling as part of that is we have a fault-tolerant I2C line, as well as a low-power 3.3 volt rail, as well as the actual the satellite shutdown signal, which is part of the inhibit switches and the remove before flight. Getting into the actual the power subsystems themselves. So we have here we have a battery card, which is actually two independent 2s lithium ion packs on a single card, and those are two independent packs in parallel. It's kind of 2s 2p, but also it's not, because each pack has its own battery management system independent from each other for redundancy. So each of the packs are independent. You get about 37.5 watt hours per battery card. And they're just boring 18650s. Nothing special about them other than the ones we use are UL listed and rated for air freight. Each card has the embedded battery management system on board. We have the inhibit switches, which are ISS compliant, which is a step outside of the regular CDS, I believe. And then, as Hayden and Marvin talked about, we have the integrated thermal insulation. We also have kept-on heaters on board. Going into a little bit more detail, I'm sorry this is such small print for the schematic here, but we have the overcharge and over discharge protection. And how we do that is we use some chips from ABLIC, the S8209s. And what those do is they have a hardware defined charge and discharge cutoff. So that's actually like part of the silicon. It's not programmable, which is nice because you don't have to worry about like a single event just flipping a bit and suddenly your cutoff is at 5 volts instead of 4.2. But you do have to order the specific SKU. As part of that, though, is these chips right here. There's actually you can daisy chain them. So what we can do there is we can actually also add in a software defined cutoff through the onboard F09. So we can actually define outside of the hardware defined ones of the ABLIC chips. We can basically cut this off at any time with these ABLIC chips through the F09 for whatever reason. Moving on, we have our fuel gauge over here, the 17205 from Maxim. This chip in particular is an incredibly precise fuel gauge. It takes into account like your depth of discharge, the age of the cells, the temperature of the cells, all of that into the actual fuel gauge calculations, which is really nice. It does that all like internally itself. It also has integrated temperature and current sense measurement sensors, and it's reporting all of that back to the local microcontroller. And that temperature that we're reading is also how we control the onboard kept-on heater. It also has a dedicated alert pin that you can actually program, which is really nice because this chip right here is incredibly low power. It's in the like tens of microamps range in terms of like active current draw. So we can basically sleep the onboard microcontroller until it gets like an interrupt or something like that. So it's much more power efficient that way. So something we ran into is our inhibit switch architecture. And what we had to go back and redesign it. And what we have here is we have two mechanically and electrically independent inhibit switch configurations. And what that does is we have these inhibit switches down here, which when they're inserted in the deployer, they're closed, they actually ground out a line that we call shutdown. And that's like our shutdown signal that goes in through the ABLIX and cuts off the batteries that way. We also have these over here that this is in the power path of the batteries. So these physical switches are actually cutting off the batteries from the bus mechanically as well. This does actually meet the spec for ISS deployed CubeSats, which is a step above what some other private launch providers need, which is it's nice to have a system that goes above and beyond there. As for the solar modules, so we have, it's 1U each. As Andrew said, we get 2.34 watts peak per module. So that's for 2 of the cells. That's also the theoretical peak. That's not with the maximum power point tracker. We have an actual active MPPT. We're currently running a perturb and observe algorithm on that. We would like to move to some more efficient and modern ones later, but perturb and observe is boring and it's dumb and it just works. As Marvin and Hayden said, it is also directly connected to the frames thermally. And it's also where we insert our RBF tag. So that is actually where the RBF goes in, and that also grounds out shutdown through the solar cell there. And talk a little bit more about the architecture of the solar cells here. So the way the short of the control loop for the maximum power point tracking, we have our voltage and current sensor coming in. It's reporting over I²C the measurements to the STM32, which is doing the maximum power point tracking calculations. And then we have this LT1618, which is a boost converter, and it is an adjustable boost converter. So the STM32 is actually applying an analog voltage and controlling the output of this boost converter. And that's actually how we're setting the maximum power point, is we're just controlling just a COTS boost converter IC. And then that's going directly through an ideal diode for reverse biasing, but then directly into the bus charging the batteries. So moving on from there, so the Orsat power domain is what that is that's not a specific card. That is a design block that has to go into each card that has to operate on its own. And what that is it's trying to provide a standard design, like a standard interface for students to interact with basically the control of the C3. So this is outside of the CAN bus. This is just to turn on and off, basically to interact with the power systems. So a standard way to interface with the power systems, and it's also so we can isolate a single card so that like a single payload or a single card cannot brick the entire satellite. It just can't pull the entire thing down. And what that OPD looks like, and this is going to, again, this is on every card, is we have an I²C interface that goes up and down the backplane. That goes into, we have a GPIO expander. So this is how our C3, which is our main onboard computer, can monitor and control each of the card's power systems. So it can go in through this GPIO expander. It has the ability to basically cut the power to a card and just remove it entirely from the bus. There is a fault line. So if the onboard circuit breaker detects a fault, it can read it through here. We also have an emergency I²C bootloader, which is actually really funny because you have I²C coming in here, and then on the output of this GPIO expander, you are bit banging I²C over I²C. So I call it I4C. No one finds that as funny as I do, but I think it's hilarious. And this I²C line is also fault tolerant. So I²C in general is very vulnerable to single event upsets. All it takes is a single upset on one slave device can basically just pull the entire bus down. So what we did to help that, we have this comparator circuit design, which will essentially, if it senses that the bus has been pulled down low for too long, it will actually cut the whole thing off from the bus, the I²C line off from the bus, and actually all the cards come off of the bus because the whole bus is low for every card, and then the cards will slowly come back up and it will either, the single event will be cleared because we power cycled everything, or we will slowly come back up and we'll be able to figure out which one is the card that is dead and the one killing the bus, and we can turn that one off for good. So it's not perfect. There are some flaws with this problem, with this design, but it's better than nothing, and it's off-the-shelf parts, and it gets around using rad-hard anything. So moving on from there, we actually also have the Max 4211, which is our current monitor, which we use as a circuit breaker. So essentially, we have the battery voltage coming in, and what this chip coming into the card, and what this chip is doing is it's looking at the current draw. If it detects a short, it will cut off the card from the bus. So it would turn it off, and that sends a false signal to the C3. It can also do that if it is just signaled directly by the C3. Through that GPIO expander, we can tell this card to just cut itself off, or it also can report the power draw to the local microcontroller. Power supplies, that is kind of up to each system on their own. So each card handles its own voltage regulation. It allows the OPD to scale and kind of apply, it allows you to scale the voltage rails to whatever your card may need instead of running it directly through the entire satellite. Our reference designs, we like to use automotive rated switching power supplies from TI just because they're cheap and they're high frequency and efficient. But it doesn't really matter. That's kind of the beauty of this part of the system, is it's isolated from everything else. So it really is up to whoever is designing the system to use a power supply that works for them. Thank you for coming. So here at the end, here's all of our source files. You can contact me directly with any questions. There's my email or my LinkedIn, or you can feel free to contact Orsat as a whole with the aerospace email. And thank you. I'm ready to take questions.
Thank you, David. And that was exactly on time. So thank you for being on time too. I can see some questions on the chat have been answered directly. And there's another question. I can speak a bit about the future development plans for Orsat power systems. What's in store?
Yeah, so I think the one thing we're working on is we're working on a 1.5U solar module, specifically because going to 2U, you can just put two 1Us together, but you can't really do that with a 1.5U. So we're debating if we should do a 1.5U or actually just stick with the 1Us on there. As Andrew also briefly mentioned, we would really like to do a silicon version of our solar module, just because gallium arsenide cells are expensive and not everyone can afford them. And if your power budget would allow it, it's really nice to be able to get away with those.
And can you talk a bit about any considerations and challenges if someone would try to scale the power system as it is right now beyond 3U?
Yeah, so a lot of problems with that come with just the card cage system inherently is challenging scaling that to 6U. In addition to that, with these solar modules, so you could just kind of like tack them on just as the 1Us, but you could also get potentially get much more power and much more efficiency out of just having like the full 6U side as a single module. That's kind of there's a trade-off there, because you are getting more power, but also you have a very specialty module for one specific situation, and we kind of like having the flight heritage and the simplicity of just having one module like daisy chained along. So, you know, that's something that we're kind of debating for what would happen if we scale it to 6U.
And finally, if you can speak a bit about the environmental considerations when designing the overall power system.
Yeah. So the big thing that we did when we did some testing with a solar simulator, which was a very janked up halogen bulb, but that was part of the testing that we did for our maximum power point tracker, because it also actually really heated up the modules to the point where it actually desoldered the modules from the board, which we were not expecting, and was terrifying because that was very shortly before flight that happened. But so, heating it up, we've also the batteries were also a big consideration in general for the thermal testing, because on our mission, they're the most thermally sensitive component. Everything else can go way below 0 degrees. So those are the things that are going to freeze first. So that was obviously the thing that we chucked in the freezer first to see and make sure that that control loop was there with the heater and all of that. I would have liked to do a fair bit more testing on the solar modules in general, just because there's a whole lot of weirdness that happens with maximum power point drift and with temperature and with the different degrees of illumination. But time crunch as always.
Oh, excellent. And I think we are on time for our next talk. So thank you, David, for giving us the in-depth overview of the power system for Orsat. And I think we will be back for Andrew. And our next presentation will be around Orsat firmware and the software architecture. So back to you, Andrew.
So this will be a short presentation, so you'll have lots of time for questions and moving on. So the software and firmware people made me do this, so I'm way out of my league, so forgive me. Okay, so let's talk a little bit more in depth about the firmware and software that we're running. Just to review, again, we have the 3 levels of computation on board Orsat. We have the distributed M0s. We have on a 1U, we've got 6 of those. And then we've got the single Cortex M4F running the onboard computer. And then the mission processors like the GPS and the Star Tracker run at Cortex A8. So again, as you'd imagine, everything's based on CAN, right? We use CAN as the communication bus. And if you don't know CAN, I won't go into it, but it's a 1 megabit per second serial bus with prioritized multi-master connection, blah, blah, blah. And we use it because, and this is a whole talk into itself. Why do we choose CAN? We didn't want to. We used CAN on previous rockets, and for reasons we hated it. So we switched to Ethernet, and we love Ethernet. Ethernet is an amazing bus, and it's very friendly for software and of course modularity. The problem, of course, is it's really, really power hungry, and it's too power hungry. It's easy to power a rocket for 10 minutes. It's hard to power a satellite for forever. So we had to cry and give up Ethernet and switch back to CAN, which is more power efficient. So we did that. And then of course we wanted the standard on top of that, so we chose CAN Open. There's some impedance mismatch between a student project and CAN Open, as those who know CAN Open know. It's a pretty heavy protocol to some extent, and it's complicated, and it's a weird way to think about things. So CAN Open goes from OSI layer 3 to 7. It's used in industrial automation, and it's really good for that. We question whether it's the right protocol for Cubesat, but it is, and it's, ESA says it is, and so CAN Open it is. The thing to remember with CAN Open is that not only does it describe the messages, but the messages exist like a blackboard, if you will, or a data structure in each of the nodes. And so when you think about, it's not just communication protocol, it's really a data definition protocol. And each node defines its data and then shares that definition through electronic data sheets and whatnot with other nodes. So when you're writing the battery temperature value, you're writing it to the CAN Open node structure, or the CAN Open structure. In our case, we use CAN Open Node, which is an open source library that implements CAN Open. And it's great because CAN Open Node runs on the Linux boxes and on the 32-bit microcontrollers. It's very lightweight and very flexible. Then again, one more thing about CAN Open: these electronic data sheets are all XML, and it's you don't want to hand edit it. So there's one of the huge, I think, important tools is a really good CAN Open EDS editor. And so that's a good open source project to really move forward on. There, one exists, I think it's called CAN Open Editor or EDS Editor, and it's hard to use, and so that would be a great project. So let's talk about the firmware a little bit. So again, we have a kind of an upgrade path, if you will. You start off with a off-the-shelf development board, move to a proto card that you can build yourself and hack to death, and then you move on and run your code on the actual card itself. The firmware is nothing special, right? It's a GCC plus OpenOCD, and we use since we're using STM32s, we use the ST-Link 3 version 3s, I think they are, the little teeny tiny JTAG debuggers. And we use GDB, and we have make targets for make write to program the flash, and make GDB to go through GDB when we're debugging. And again, all that through that flat flexible cable interface. We have a really interesting way of doing the firmware. We don't have a firmware repo per project. We have a single firmware repo, which has gotten us into trouble a couple times. And then we use branches for development on each thing. The C3 onboard computer, which is an M4F, it shares the same repo as the M0s for the solar and the battery and whatnot. And both run ChibOS, so we've got ChibOS as a external submodule, and CanOpenNode as an external submodule, and the M4 requires a file system for the 16 gigabyte eMMC, and that is little FS, which is a great tiny little embedded file system. So we can do over-the-air firmware updates. So we have L-band uplink and a UHF downlink. Actually, we have UHF uplink as well, and we can send files up using CCSDS protocols, not yet FDP, so we're excited about the Libre Cube thing. So we've got our own terrible little protocol until we finally implement FDP. And that file is stored on the eMMC, and then the C3 can grab that image on a USLP command and program its own flash. We have 2 flash banks on that STM, and so we could switch back and forth. Right now, we're looking forward to the first over-the-air firmware update, which will have more ability to switch back and forth between banks. And then finally, the M0s have a built-in CAN bootloader, which is part of our firmware repo, and we're very proud of it. It actually mimics a hardware CAN bootloader that's built into the STM. So as we upgrade those STM chips that do have the hardware bootloader over CAN, it'll just work seamlessly. But right now, this is a software bootloader that just mimics that hardware bootloader. Right now, we don't have the functionality for the M4 to program the M0s over the CAN bootloader. That's the next over-the-air firmware update. So just like every good open source Cubesat project, we have shipped it with only the bare minimum functionality. Oh, it's painful. Software. So let's talk about the software that's running on the Cortex A8 boards. So again, we have 2 levels of tools. We have the commercial off-the-shelf development kit you can buy for $35, and then we have the actual boards themselves. And Pocket Beagle is amazing. It's from beaglebone.org, and they come up with a bunch of kits and software infrastructure tools that we use a lot. So on each of our A8 cards, we have this sort of architecture. We've got obviously Linux, and on Linux we have something what we call the Orsat Linux Manager, or OLM. OLM interfaces that cards to the CAN bus, and it runs the Orsat Linux Updater, which allows us to update the local Linux distribution, and then it also interfaces directly with whatever card application is running. And so this is really the OLM the OLM is really the interface to the rest of the application. So we build our own Linux images. It's just easier because we've got some custom stuff that we do. We use the BeagleBoards image builder to do that, and we generate a custom image for each of our cards. That's all posted, and you can get much better information about this whole software system using Read the Docs, which we posted, and it's a really great system. Oh, and of course, we burn these images directly to the eMMC, despite the fact that each A8 card has a microSD card as a backup. We don't want to fly on the microSD card. Of course, we fly right off the eMMC. So the Linux Updater is a pretty neat little custom solution that we have because we knew we were going to be limited both on the file upload side on the radio link and on the CAN bus. So we create these updater files, which is a tar file that's got the .deb file. Again, we're based on Debian Bullseye. So we use deb files to update the software, as well as bash scripts to run those deb files. all the output from that is put into a status file that then gets transmitted back down, so we know how the update went. And it also gives us a full versioning of all the Debian packages on board. So it makes a large pile of output messages, but now at least we know what's happening on board that particular card. So we use we wrote our own program called Update Maker, which takes the deb packages and whatever else we've got to update, and using a CLI creates this tar file essentially. And then on board the card, we've got the Linux Updater, and that actually runs a Python daemon. And by the way, the Orsat Linux Manager is also, everything's a daemon basically. And the Linux Updater actually runs through the bash script and in the our file archive and runs everything. And of course generates the output files. So Olm is the basis for everything. It's a C-based daemon that is our front end to the CAN bus. It's started by systemd, and as you'd imagine, and basically really it abstracts away the CAN bus from the application layer, which is really important because a lot of the application layers are pretty complicated. They're their own huge software infrastructure project. Anything we can do to kind of abstract away the details of the satellite for them would be great. And it also acts as sort of a monitor for each of the Linux boxes and transmits what's going on in terms of CPU usage and RAM usage and the percentage of the eMMC being used. So we really like the Octave chips. They're based on the Satara AT335X, I believe it is. And they come with this thing called a PRU, a programmable real-time unit, which is a single instruction per clock, 200 megahertz deterministic processor, which is kind of weird, but it's amazing because it allows us to write our own custom FPGA-like interfaces to our local hardware. So we call it PRU CAM because in our case, we talk to the AR0134 image sensors, to a shortwave infrared star tracker, and sorry, not star tracker, a shortwave infrared camera that we're using for a climate science mission. And we even use it for talking to the software-defined radio GPS receiver, which has a very weird 4-bit parallel data stream coming out. And we can program a custom, basically, protocol interface for each of those different peripherals. So like we mentioned before, everything talks through this FFC connector. We can talk JTAG and we can talk USB, and the USB, when you plug it in, it can either be a serial port or it can be a USB Ethernet port. So super easy to debug. On the outside of the satellite, we actually have a debug port that talks serial directly to the C3, so we can send it commands. ChibOS gives us a command line interface shell, actually, which is amazing, and we can talk directly to it, as well as CAN, VBus, and shutdown. And again, we saw the FlatSat before. That's how we do all of our software integration testing. And finally, wrap up with CANopen Monitor, which is a ncurses-based display of CANopen messages. And this is great because we can see what's going on in the bus. We can see heartbeat messages. We can see which nodes are up and running. And you just plug in the EDS and DCF from CANopen, and it decodes the messages on the fly for you. That's another open source project, which we highly recommend because we haven't seen anything else that does the same thing. And that's it. Thanks very much.
Thank you, Andrew. That was really nice and exactly on time, so thank you for that too. Yeah, there have been a few questions on the chat, but I think that those were already answered here. Here's another question. We can see you're using F0 and F4 and A8, and being from a systems perspective, like having such a diversity and heterogeneity, right, of the processor might be challenging. Like, how did this work out for you? And would you recommend it or do it again?
Maybe. Yes. Yes, we made all the right decisions. None of our decisions were terrible. So that's a really interesting question. We like the F0s. I think the F0s were a win. And the distributed F0s, you talking over CANopen, I think are simple enough for a student group to deal with. The C3 is too complicated for a single student group and is hard. And we all know that embedded systems engineering is hard. So one of the things we might have done, and we may do in the future, is move our onboard computer from an M4 to an A8. Because being able to run Linux as the onboard computer would enable A, more CS students to participate, and B, allow a little bit more heavyweight threading and processes and modularity in the code, and be able to, again, that modularity is key, right? We all have these giant, complicated, interdependent systems, and it is so hard to debug. That M4 is very hard to debug, and RF is hard to debug. So whatever you can do to break that apart and modularize it is really important. And it may be that in the future we move from the M4 to the A8 specifically for the flexibility and debug capabilities of Linux.
Despite the difference in power consumption, right? Like, you think that this is still tipping the scale, the debug advantages?
We'll make the electrical engineering kids cry by running an A8, but you know, they do have low power modes, and they don't have to be on all the time, so it's not terrible. It's pushing it for the reason we didn't do that in the first place is it's pushing it for a 1U. It's not pushing it for a 2 or 3U. But a 1U, it's a little dicey to run that A8 all the time. So maybe one of the things that we'll look at in the future is some kind of hybrid architecture. I know that Octavo now has a Cortex M7 that runs, or I think it's an M, actually I don't know what it is, sorry. That is the hybrid architecture where there's a local low power and a high power Linux box, and they work together. And that may be more complicated than we can handle, but it may be where we can shut down the big thing, have a little thing work for a while, and then, you know, power cycle the larger processor. That hybrid architecture.
Cool. And if there is a question here in the chat about do you have a power consumption record per OTA update?
No, we don't. We don't expect over-the-air updates to take that much power. We're always in receive mode, and it takes very little power. I think it's like, let me calculate that. That's about 30 milliwatts, I believe, of continuous power to receive. So receiving is not hard. And then again, we've got that local 16 gigabyte cache where we just dump all the data we receive from the ground, and then we don't have to wake up the thing that we're updating until we've got the whole packet and we're ready to update it.
And then a final question would be about, there's been a lot of comments about CANopen, like through your talks, and the choice of CAN, and specifically CANopen, right? So with all its shortcomings, you know, and possibly the lack of alternatives to some extent, right?
That's exactly
yeah,
it.
That's
someone just told us about CAN-TS for the first time a couple days ago. I've not heard about that, but that's apparently a more lightweight version of CANopen. But I almost don't trust it. CANopen is so well supported and so out there and such a well-defined, to some extent, protocol that it just makes sense, despite the fact that it's heavyweight and it's hard to teach and it's counterintuitive in how it uses the CAN bus and everything. I still don't see an alternative to CANopen. I wish there was one, and maybe CAN-TS is one. I've not seen it.
And I can see Agis here on the chat questioning the selection, whether you have considered UAV-CAN, so UAV-CAN.
No, we've never heard of it. So we'll go look. Thank you.
It's well supported and prolific right now on a different domain, which is the UAVs, but there's lots of similarities, obviously, right?
Yeah, absolutely.
Yeah.
That's great. We one of the things that we try and do is steal as much as possible from people who have the same problems that we do. So UAV-CAN will be super interesting to look at.
Cool. And if there are no other questions, I would like to thank once again Andrew and the whole team of Orsat for this lovely session that we have. And there's a few more Orsat talks tomorrow, so be on the lookout for that. And with that, I think that that concludes our session for now. and we can jump into the next break. So thank you once again, Andrew.
Thank you guys. I really, really appreciate
Thank
it.
you.
This is fantastic, and we're happy to be here.
So for the break, we're going to be once again breaking up into different rooms, and Andrew will try to duplicate and clone himself into multiple different rooms, apparently, on room 1 and room 4 at the same time. I don't know how this is going to happen, but I'm sure there are going to be enough of Orsat people around to be in different rooms, right? So make sure to.
Dimitri will be taking the firmware room for me.
Cool. That's great. Thank you, Dimitri. And yeah, we have room 1 for Orsat system, room 2 from Orsat mechanical, room 3 for power, 4 for firmware, and of course, there's always the room 5 lounge just to hang out and yeah, chill. And we will convene back here in 20 minutes from now, sharp, for our keynote. So see you all around.
All right. Hello, anyone here? What a good timing, Dmitry. Right.
So, welcome back to the main room. And I've seen that, in particular, the room 3, the power room, was quite busy. So I hope there's a lot of questions being answered in that power regarding the Cubesat power system. And I'm happy now to be here and introduce you the keynote. So let me find the slide. So we're here. And I'm very happy to have here Pauline Faure. I hope I pronounced correctly. And Pauline, she's a faculty in the Cal Poly Aerospace Engineering Department since 2018. She has obtained her PhD from the Kyushu Institute of Technology in Japan. So I assume you also speak a bit of Japanese now?
I do.
Wow. But your program that you have established, you have still given it a French name, Etoile.
Yes.
And so this program, Etoile, you're going to present it to us now. But in a nutshell, your focus of your research is on the adoption and usage of space systems as an educational tool to support local communities, to build capabilities and support sustainable space activities. So that very much goes in line with what this Open Source Cubesat workshop is also about. And so in addition to, or really to support your research vision, you have established this Etoile, which is a research laboratory dedicated to the development of educational technologies for open and interactive learning via the engineering of small satellites. So, I mean, your students can be so grateful and thankful to you that, well, you give them everything that they need to build satellite, and also in addition they get credits and they get their degree. In total you have like around 40 undergraduate students right now and 4 graduate students, so I imagine you're very busy. So I'm double thankful that you're here and giving this this keynote lecture. Also it's your morning, so good morning. And without any further words, I hand over to you, and we are all excited to hear your talk.
All right. Thank you so much, Roger, for the kind introduction. And yeah, good afternoon, everybody, or good morning, or good evening, depending on where you are. Yes, I'm Pauline Faure, and I went with a bit, I guess, a controversial title of asking whether university CubeSat programs are a pipe dream. Am I able to control the slide myself? Yes. All right, so first a little bit of introduction. I'll be brief because Arthur did even a better job that I will do myself, but this is me at a glance, and I was counting last night, so it's been 12 years I've been doing small satellite programs at university, and it's about a third of my life, and so then I had an existential life crisis. No, I'm just kidding, I'm fine. But bottom line, I've been doing this small satellite at university for over a decade. And that's the overall timeline. And then I don't ever do a presentation without introducing my bunny. So here is a cute picture of my little bunny. Then for those who might not know, so I work at Cal Poly, which is a short for California Polytechnic State University in the city of San Luis Obispo. And I am part of the aerospace engineering department, which ranked second last year, or like this year, as a part of public and private undergraduate institution. And in that department, something interesting is that we have about 500 students total. And something to note is that Cal Poly is not a PhD granting university, so that's why our undergraduate student number is so much higher than our graduate student number. And in aerospace, actually 2 students out of 3 choose the astronautics concentration. And something fun, so to speak, is that in the department we have 10 tenure track faculty, but really out of these 10, only 2 are dedicated to the astronautics concentration. So that gives us a lot of work between me and my colleague. And overall, it's actually the one of the biggest, if not the biggest, aerospace engineering program here in California. So that's kind of an impressive feat. And then a little bit on the laboratory that Arthur said I created. Yeah, it's called Étoile. I'm French, so it's a French name. I went there. But it also is a nice acronym for my vision and my intent with its laboratory is to create these educational technologies for open and interactive learning using small spacecraft to do that. We have different projects going on with different partners. Something I'm going to focus on today, asking whether it's really a pipe dream to have University Cubesat program, is to focus on those controlled spacecraft platform for educational purpose. Also have a flight mission going on called Orsat. I told myself this was my last flight mission at the university. Maybe if I go to the industry later on, I'll do another flight mission, but within the university, I'm deciding this is my last mission. It better work. And this is what we're going to talk about of the difficulties of to make this flight mission at a university. All right, so that was a bit of the introduction. So next, let's dive into the topic of this University Cubesat program. And first, let's focus on the dreamy part of it and the excitement of it. So for those who might not know, and that might be a bit, I guess, a shock for those who know me being at Cal Poly, but Cal Poly is, sometimes I refer it as the cradle of CubeSat or the pioneer of the aerospace revolution in a sense, and all the ecosystem that it brought. Why? Because Cal Poly, in collaboration with Stanford back in the early 2000s, and developed the CubeSat design specification, which is the de facto standard for the development of this CubeSat. And hopefully, or I want to say fortunately, or maybe for some of you, unfortunately, depending on your opinion of it, use it to develop your CubeSat to be integrated in the dispensers and make sure that this is done in a safe manner. And until last year, until the data of last year, there's been about 1,500 CubeSat that have been launched. And so this CubeSat have had a huge impact, and not just on the US or just on the what used to be let's say the space powers like Russia or previously USSR, US and Europe to a certain extent. But really, it has impacted the whole world thanks to this CubeSat. And so I went through the Union of Concerned Scientists. They have a satellite database. And something very interesting is that we can see that there is a shift, especially from 2009. Here I use 2004 because this is the first publication of that CubeSat design specification. And if we look at that date until like today, or the data was until the end of last year, we can see that the number of countries owning a satellite kind of exploded right when CubeSat and small satellite aspect were also exploding. And so there have been 71. And if we take a closer look at those 71, we can see that out of those 71, 20 of those countries, their very first satellite was actually a CubeSat. And so that's very interesting. And you have different programs throughout the world. Japan, the Kyushu Institute of Technology is one of them that favor the development of space technology in collaboration with nations that may not have a space program early before that, but help them develop those programs and develop their first country satellites, for example. I forgot to check the chat. All right, and then if we take a closer look at the impact of this CubeSat, and it stemmed from university, and originally it was to provide that hands-on activities to the students and provide that first-hand experience of launching into space. But that it has developed into something more than I'm sure Professor Puxbury or Professor Twiggs may not have foreseen 20 years ago. So if we look at the evolution of the type of mission from their early inception till 2019 on that graph, we can see that there is a shift, and it's not only used for Earth imaging here or education, but there's also a shift to science, right? Early on, Cubesat and university developer were looked at, oh, you're cute, you're making a toy and you're going to launch it into space, and you're going to be the Sputnik and just get the beacon of the beep, beep, beep of the satellite and be happy about it. But through the miniaturization of electronics and the improvement of that capabilities with being miniaturized, then Cubesat have shown their capabilities of either technology demonstration or contribution to space sciences and engineering in general. And the graph on the right-hand side, I took that from an article from Space News, and it just showed the investment into space startups. So not just for Cubesat, but any space startups. And a lot of them is driven by actually launchers. But launchers have been developing, like Rocket Lab, for example, for adapting to the smaller payload, launching maybe more often, more of them into once, so to bring the cost of that launch down. And there is a clear elbow around the 2010s, and that's just been exponential there. So will we reach some kind of plateau later on, or is it going to increase? The future will tell. But the investment is booming. So I guess if you're thinking of a startup, maybe now is the time. There is no time like now. So now let's see the other side of the coin, right? And yes, Cubesat and their development have created a lot of good opportunities and an ecosystem, but there is not such a dreamy part to it too. So in particular, if we look at a university-based program, here I use this graph from Michael Swatwood, who is a researcher at St. Louis University. And he has a database that you can access easily. If you look in your browser, if you type the name and Cubesat database, it will come probably like the first result. And on the left-hand side, we can see the mission from 2000 to present. So it was until the data was until 2021, I think. I forgot the last months that it took the data, but it's really recent data. And on the left side, it's like for all the Cubesat mission, excluding constellation. And what it shows is what is the status of this different mission. And we can see that first there is quite more than a quarter of unknown. And then we have a little bit of dead on arrival at 15%, some early loss at 8%. Nothing, I want to say, extravagant that seems about right for those Cubesat mission. But if we take a closer look into what is being called hobbyists, which is organization or sometimes individual that do satellite for fun, it tends to be just one satellite. Then the number, especially like for dead on arrival and early loss, combined with the unknown and the launch failure, increased to almost 3/4 now of that pie chart. And so there is clearly something happening, and you can read different paper from Dr. Swatwood. There's a different range of reasons for that, including when you're hobbyist, doing something the first time. None of us do that really good, and of course we all learn from our mistakes and then improve from them. But when you do something only once, of course your risk of failing in some aspect is high. But the other thing is that most of these hobbyists as university, and sometimes it might be the same university, but different groups within that university. And so here I took from a paper published by Dr. Honore Livermore that was a paper kind of like on project management of a university-based satellite program. And I'm extracting the challenges from those, which are knowledge transfer, variety of duties, feeling of ownership, and documentation. And that resonated very much with me and probably with some of you too, if you have developed a CubeSat more than one time. And then looking at those, I was wondering, okay, so ideally, what do we somewhat all know that we should do to prevent those challenges to happen or be minimized? But then what is also the practical situation of those challenges? And so if we look at knowledge transfer, one of the things is at university, we really want to tie that with the curriculum of the students to force them, so to speak, to be involved in the project and be motivated to give a result at the quality required in the time frame required. And so what that means for that university depends on the type of university. For Cal Poly, non-PhD granting university could be senior project or master thesis, for example. However, not all aspects of a satellite really is worthy of being a senior project or a master thesis, right? There's still other criteria that we need to fulfill to make it worthwhile of the student time and I guess the reputation of your program to make it those. So the other aspect is if we want to ensure knowledge transfer, it's maybe to have permanent professional to support the satellite program. So that is great, ideally, but that's not practically always feasible. Why? Because we are the one who costs the most money. And a lot of times those CubeSat programs tend to be running on very low cost. So what that means is that we cannot pay the people. We cannot even pay the students. We cannot pay even less professionals, or you need to have other scheme going on. And it's an additional hurdle here at Cal Poly just because we're a non-PhD granting. So really our main role is to teach. And then we have all the variety of duties, whether it's on the faculty side or the student side. None of us, our main job is to do a satellite. We have to go to classes, full class load, and a lot of students also have to work outside, for example, just to support their education. In the US, it's extremely expensive. Here at Cal Poly, a year is like $30,000 to $50,000 a year. So it's very expensive. Then we have the feeling of ownership in the sense of, because we have small form factor, and some of you talked to that during the workshop, like we want to combine that into at the least number of printed circuit board. But when you do that, usually what I've noticed is that one printed circuit board is one person. So if that printed circuit board has different subsystems on it, that person can really feel overburdened and overwhelmed really quickly. And so from an educational standpoint, that's not great because you don't want to burn your student that you're already not paying, that do not necessarily get credit, and then they do that work for you on the satellite project. So you want to be very mindful of that and find that right balance. And then documentation is kind of my favorite in the sense of, as engineers and especially students, we know it's not the sexy part of making a satellite, right? Nobody really wants to write those procedures, keep in mind what we did wrong and why we did it wrong, and keep that in mind, right? We want to solder, we want to put things together, we want to go to the vibe table and all of that. So it's an everyday battle. So, and overall, really what happened at university is that we don't only teach the technical aspect of even what is a satellite, what does that do, and what do we choose, a maximum power tracking, electrical power subsystem versus a direct energy transfer, for example. But it's also teaching them to be professional, and if you don't come on time, it's not okay, or if you cannot complete a task, it's all right, but you need to give a heads up more than 1 hour before the task is due, and all this other aspect that goes into a project management. So that's kind of the part of the non-dreamy aspect to it. So the question is, okay, so now I kind of picture that the two aspects. So where do we go from there? And so for me, it goes back to the fundamentals. So when I'm lost, I always go back to the fundamentals. And for a university, I strongly argue that our role is really to educate. And we don't need to launch a spacecraft to educate. We have capabilities to simulate that experience of the full life cycle of a spacecraft without launching it. Launching is of course very exciting, and to put something in space while you're at school, I've gone through that myself. It's really exciting. but it puts a burden on the students. It has a cost that cannot be ignored. And for some program, it might be okay. And for some program, it's less okay. And so it really depends on all that dynamic. So next is, this is where I'm going to make the case for not stopping Cubesat program that fly missions, of course not, but making a case for educational control spacecraft platform. There are different endeavors going on throughout the world. Of course, I'm going to talk about the one I know, which is the one we are developing here at Cal Poly, which is called Akio. Akio means star, so I have a star. I have a star theme going on here. It means stars in Chumash language, which is Native Americans' language on which Cal Poly has been built. And so really what that aims is to bring that spacecraft to the classroom, to train the student on it, to be okay with it being broken without having the stress necessary to launch it, to comply with those launch requirements, the range safety requirements, or to comply with licensing, for example, aspect, and all these other aspects that we might not know the first time we go to the Cubesat programs, but that needs to happen and that are a burden on the development, whether timeline or even in terms of cost, knowledge acquisition. All of that plays into the development of a full flying mission, and that's non-negligible. And so I keep clicking on my arrows, but I need to click on the screen here. Sorry. So here, and if you want to read more about that, I published a paper for the SmallSat workshop over the summer that is accessible through their proceedings, so you can read more about it. The idea is we have this different subsystem on the flight segment aspect of a spacecraft. And then at a university, with that, we have that other dimensions of the university being divided into colleges, and then each colleges has a different major. And so I was looking into here, especially in Cal Poly case, but I think a lot of the teaching notions is common throughout the world. What do we have to teach in electrical engineering or computer engineering or aerospace, mechanical engineering, material engineering, and any other engineering, or even outside engineering? We could also go to the College of Liberal Arts and look and talk about ethics or space law, for example. But looking at those, how could we relate some of the fundamentals that need to be taught in this discipline to a satellite platform, whether it's the electrical power subsystem, structure, communication, attitude, thermal, and whatnot. And we can see that there is application for that platform. And so there is a way where we could include that platform in the curriculum, not only for aerospace, because at the end of the day, spacecraft are multidisciplinary, so we really need to work together and benefit the students, not only because they join a special research laboratory or club, but really being part of their own curriculum. While they are already investing so much of their time and their money, especially in the US, in their education, they could have that full hands-on, learn by doing experience throughout their 4 years or so of college, for example. And then there's all the other aspect, not necessarily related to the flight segment, but related to its interfaces. So the ground segment definition. Yeah, how do we communicate with satellite? How does mission operations look like? Do we send a comment? When do we send those? How do we get data back? The launch vehicle aspect, all the regulations with the licensing or orbital debris. And then anything outside of that, such as systems engineering or project management. Project management and system engineering, for me, I teach, for example, systems engineering officially here at Cal Poly. For teaching it, it's words on the slides. People don't always understand it, but people don't understand it until they actually have to practice it. And so you really need kind of that side project to go through that so people understand, oh, I should really write my requirements before defining a solution. Now I understand why people have been telling that to me for the last year or so. Because yes, as people, again, we are more excited about doing it than actually planning for it. And so we want to go directly into the solution. And then when we have it, it's like, well, wait a second, what are my performance that I'm looking for again? Is that actually the design that I designed against for this performance? And then oftentimes we realize that no, if we haven't have our requirements, for example. So there's that whole ecosystem really that can be into that platform that can be adapted to college education while being mindful on everybody's time and capabilities, and kind of reducing that stress of we have to comply by a launch date or with really particular range safety requirements, for example, that kind of are extra and are good to know. But at the same time, that does not make you a bad junior engineer if you graduate and do not necessarily all the nitty-gritty details of it. At least I would argue that way. All right, so here is just a glance at the first version of that platform, very bare. And so right now it's a structure with an electrical power system board and a multifunctional integrated payload processing module beefed up, because at that time we don't have an onboard computer or command and data handling system. So it's kind of mixed between the two. And then in terms of where we at, it's funny because I also had to revise my expectation, right? Myself, being an engineer, I tend to overestimate what I can do within a year. And so at first I thought that project, will be done within a year. But here it started 2 years ago now. And yeah, we are not done. We just completed Mach 1. And now we're working toward Mach 2 and future versions. And we are very early on into that process. But again, that goes back to learning how to manage your time, understanding the constraint that the students you're working with go through, and managing all the expectation on both sides. So, but that's a fun process. Yeah, thus far there has been close to 30 undergraduate students being involved over the last 2 years, and 1 published master thesis and 2 in waiting master thesis. So hopefully it gets published and then that can be shared. And then eventually putting everything on the website that I don't have yet. So for any people in the community to be able to take a look at it, for example, and just use it as they want, manufacture the structure if you want with your 3D printer, that's possible, and all that. And create your own little star. So in a brief, since I'm starting to eat in my margin of talk here, just the lessons learned for that my last decades, in brief, no worries. So it's really making a spacecraft is not easy. I think we can all agree to that. It's a multidisciplinary in nature, and it's particularly not easy at university because of the different challenges we talked about earlier. Nobody is full-time. The students are not even officially engineers, so we have to, and they all can come from when this is their first year at college to their last year at college. So there's that wide span of knowledge. You have to do continuous training and teaching and remembering that, right, first year of college, I didn't know myself what actually a satellite is and what it does and what is the guts of it, right? It's really rare for us to see even picture of satellites inside of satellites. So there's all that dimension. Then there's also the other aspect of if you do a flight mission, you need to make sure that your university can support you. And any country has export control regulations. It's particularly strong here in the United States. So we have really to be careful of what we publish publicly and what we really cannot publish publicly, because none of us want to be fined or go into jail. And then there's the other aspect of, as much as possible, tie this project to the curriculum of the students being involved. Can they get credit over a quarter, 2 quarters, 3 quarters, or semesters, depending on your system, just so that they don't have to somewhat invest extra time outside of already their full course load and sometimes their other job that they have to pay for to be at school. Another thing that I think is really important is do our best, and of course it's easier to say than do, and I know that firsthand myself, to get the funding for those students in there, not only for summer or breaks, very important, because now the course load tends to be lighter if non-existent, but also during the school year, again, to just, so maybe they don't have to work 3 jobs outside of their education, but maybe they can work on that project, gain that knowledge while also being paid, so they can really better focus while being less worried about funding, for example. And that also goes for the faculty being involved. for example, buying units, so you teach a bit less and can focus more your energy toward the teaching and the mentoring of the students without burning yourself down, because you also have to spend 20, 30 hours in a classroom beside your research. And then, yes, in the past year, a little sprinkle of additional fun is the IC shortage, which make it really difficult to do any development. The number of times my students come is like, oh, I have the design, it's ready for manufacturing, and as like 1 day later, we are trying to put the order, and now we have all these chips that are not available and cannot be found, and we need to redo the design, and it just go for weeks and weeks. So it's kind of fun, so to speak. I have a weird version of a definition of fun. But what that means is that we need to adapt to that, and we need to revise also our strategy when we develop, and be a bit more flexible on that aspect. So just something to keep in mind. So in summary, if I go back to the original question, is it a pipe dream to have these university CubeSat programs? It can very much be by underestimating the quantity of work that needs to be done, right? It's not just about doing that spacecraft or just that printed circuit board. There is way more around it, especially if you do a flight mission. And then as people, we tend to overestimate the number of hours in a day. Yes, they are 24 hours, but we also need to sleep for some of them and even eat. And then the other constraints that each individual has of the people involved in that project. But it doesn't have to be. It could actually be just the dream, and going back to to being more educationally oriented, right? And so this is kind of my call for those controlled educational spacecraft platform. And you can use that, you can teach these notions into your classroom or do a spatial training. And I would really argue that that will also foster that knowledge retention for different type of learners, right? Some of us are really fine with just PowerPoint. Some of us really need to put our hands into it, do the mistakes, and then be like, oh, that's what that meant, that line on that PowerPoint. And then there's a lot of talk about, I feel like, diversity, inclusion, and equity going on, and being more mindful of the diversity of people. But when you force students to go through a research lab or a club to gain that practical hands-on activity, you're really eliminating all the other students that have to work beside their classes to actually be in their classes. And of course, that's not something true on different countries, because the cost of education is wildly different. But there's that large gaps, and especially it's been really shocking and striking to me here in the United States. So ultimately, there is a better case for using that into classes. So there is that large number of students, hundreds of students, that can be trained to that and have that hands-on experience against the tens of students that join a particular laboratory or club activity. All right, and that's it. I made it to the end. I'm sorry. I guess I ran a little bit behind the original schedule. And I'll take any question if there is any.
Thanks a lot, Pauline.
Pauline, this was plainly amazing. Thank you very much. And there's some time lag, but I would like to hear everyone giving a big round of applause. Yeah. And it's helpful if you put on your microphone and we can actually hear you. My God, I have to breathe. There's so much information that you packed in this a little bit more than 20 minutes. And I think I will have to watch this recording over and over again, because really a lot of information. And you got me with the slide that said you don't have to launch your CubeSat into space, because I totally support this. It's really cool and fun to build a CubeSat, and you learn so much. But you don't need to send it really into space unless you have a good mission for it. But it's also, you can put it on a balloon or put it on Mount Fuji or some other big mountain. And you can test out, as you mentioned, you can test out everything, sending the commands and the operations and the engineering. Yeah. So Let's see. Do we have questions from the audience? We have something in the chat. There was something about do we have statistics on Polysat missions? I don't know how much you would know about those.
Yeah, I was monitoring and I saw
it's a
people
bit
responding at the same time, so that was good.
topic. Here, are you in an analog astronaut house? What is that? Red is out.
Not yet.
I wonder. You like open roof, but you have books. It's kind of
Yeah, like Mars 500 mission type thing. I am not. Or not. I'm not sure I would want to be though. I would miss my buddy too much. Can my buddy come?
There's another question from Gyro.
Yes. So how do I deal with the high turnover rate of the undergrad students? A lot of organization and logistics. Frankly, it sounds very cliche, but yeah, 80% of the work is actually a lot of organization before doing anything. And so plainly or like practically the way I do that is I have a roster of my students and I record the year they are at, what they are working on, and when they do plan for grading, not grading, sorry, graduating, forget a syllable here, graduating, and then based on that, when I see they're going to graduate maybe like 2 quarters, like I try to on Cal Poly side we are on a quarter base. That's why I keep talking about quarters. But so every quarter I kind of go back through that, and if I see someone is going to graduate in 2 quarters or even like 3 quarters ahead, I know it's time to start doing recruitment. So we have that mentee mentors aspect, recruiting someone junior that they can be trained with that senior person. And then by the time that that person graduates in 2 or 3 quarters, they should feel confident enough to take the task on by themselves. Though not really by themselves, because I have a rule that for any sub-teams, I want at least 3 people. Number 3 is my magic number. So thank you for the question.
Okay. Sorry, I was kicked out. My machine crashed. My computer was also overwhelmed by this abundance of information. But I think Retty already is ready to take over, and we're going to the. So thanks again, Pauline.
Thanks a lot, Pauline.
Yeah, thank you for having me. Thank you for the great workshop.
Pauline for merci.
We're handing over now to Red for the lightning sessions.
Yeah, yeah. You can stay around. Okay, I'll take presenter. Right. So this is the lightning sessions. I hope you're all ready. We'll start with Jan Mas. You have to get ready quick. Just start your camera already, Jan. And you each one of you has 4 minutes, and I'll be timing that. And you're standing. That's very good. At the end of each session, I will ask everyone to turn on the microphone and give a big yes or a small yes if you like, or if you do not like what's been proposed on this lightning topic. So, Jan Mas, you know what to expect after your 4 minutes. So here you go with your topic, which is new opportunities for student Cubesat teams with the ESA Fly Your satellite. So take it away.
Yeah, can you make me presenter that I can share the slides?
And I'll give you presenter role. That's it. You're there.
Okay, so I'm not using my own slides now. Okay.
As you want. As you want. You can share your screen. The others are warming up. Yes.
Let me share my screen. And then we start from here. Perfect. So good afternoon, Red, thanks for the introduction. So I'm working as a young graduate trainee at the moment for the ESA Academy, and I'm going to share some new opportunities for students that are eager to send their own spacecraft to orbit. Before we get to these opportunities, quick mention on ESA Academy and Fly Your Satellite program. So what the ESA Academy does, it's the branch of ESA Education Office that is targeting university students, and we have a range of hands-on programs, courses, workshops, training weeks to complement the university curricula. One of those programs is, of course, via satellite, and we try to transfer expert knowledge to the students, experience and best practices to prepare them for their careers. And at the same time, we try to increase the mission success of Cubesats, which we have seen before can be an issue. How do we do that? We support them through the life cycle of their Cubesat project. We give them expert support, so mostly from STEC, for example. We give them opportunities for environmental tests. And finally, if everything is done sufficiently, then we give them a launch opportunity. So here are our new opportunities. We are launching the fourth cycle of Libre Satellite. It's open now for proposals until February the 6th. We are going to offer next year a design booster. That is a fixed 1.5 year long program for teams who are in an early design stage and for teams that want to test their own self-built hardware, their project. We are going to offer test opportunities, 1 year in duration, where they can bring the hardware, test it, and learn how the whole test procedure is done. Besides that, on an ongoing basis, the training and learning program is always there for additional training courses, such as the Cubesat Hands-on Training Week, where we use similar hardware to what we have seen with Arico. So now to Flyer Satellite 4. It has been changed a bit, the scope of the program. We're targeting now this time teams that ideally have already consolidated design. You see, we are planning to start in Q2 2022, and this should take 2 to 3 years in total. The earliest launch opportunity foreseen is in 2023. And we are having next week and in mid-January, we're having 2 online information sessions that you can join, and I will you'll have the link here in the presentation, but I can also join and share them later in the chat. To be eligible, has to be a 1, 2, or 3 use space per Cubesat, and it should meet the requirements of the Flyer Satellite Design Specification version 4. This FDS can be requested online. It must come from an ESA member state or associated states university and has a core team of 8 eligible students. It has to have a designated professor, team leader, and systems engineer. University is fully responsible for the Cubesat. It's not going to be an ESA mission in the end. So if you would like to join, what do you have to do? Please submit your proposal, fill in the proposal template, provide endorsement and funding letter from your university, and all the details can be found in the link and the QR code that you see on this slide. So we would like to hear from you. Please join one of the information sessions. For any question, contact me during this event. Contact us via cubesat@esa.int and follow us on social media to stay up to date. Thanks a lot.
Thanks, Jan Mas. Thanks a lot, everybody. A big round of applause. So, Jan Mas, for this 4th edition of Flyer Satellite from ESA, I mean, who is here to give me a yes? Turn on your microphone and just shout yes after those 3. This countdown of 3. Turn on your microphone. 2, 1.
Yes!
Yes! Yes! So
thanks a lot.
Please contact Jan Mas if you need any information, and especially that link that is just here. And there you go. So next up we have Yaro Rodriguez. I hope I pronounced your name correctly.
You did, yeah.
Yeah, great. Okay, you updated, not too good, okay. You updated your presentation, so I make you a presenter, so you can start sharing your screen. And Yaro, I'm trying, right? Is from Costa Rica, and is going to present Arena, this single board comms and OBC module. So the stage is yours, and you have 4 minutes, like everybody.
And
there you go. Well, hi everyone. Thank you for having us here today. We'll keep this as short as possible. So we drew the inspiration for the idea. We are going to talk about it a bit from like 3 different places. First,
excuse me, could you speak louder?
Oh, sorry.
Closer to the microphone. I don't know where it is.
Yeah. Can you hear me better now?
A little bit, yeah.
I wonder what's happening. Okay.
Good for me.
Okay,
Good,
so again, sorry. With the inspiration for the idea, we're going to talk about it a bit from 3 different places. First, our involvement in the IRASU project, which was Costa Rica's first satellite. It was a very simple, very basic 1U Cubesat store and forward mission. Then my work on setting up repositories and reviewing the documentation for BRICS, the QTech Institute of Technology BRICS 3 and 4 bus used for their satellites. And also, we really like the excellent work done by the people at Vision Space Technologies on their BST-104 boards, which actually uses STM32s, which is important later. So after seeing all of this, we thought that it would be a good idea to develop a single board OBC and comms combo, basically, using this microcontroller, the STM32WL SoC. This module has an SX12 series LoRa module embedded to the MCU on a silicon level. So it is a very efficient interface and simplifies a lot the hardware design, the PCB design. So it is true that it is a very low bandwidth protocol. So we are looking to use it mainly for like beacons or commands or very small payloads, hoping that it's going to be there's going to be a secondary comms system for like imaging or their bigger payloads. The main benefit we see from this board is the reduced time taken by having the 2 subsystems, the OBC and the comms boards, being merged into single PCB instead of being divided in 2, which in an 1U Cubesat like IRASU can be a very big deal. So the BRICS bus, the BRICS satellite, actually has the 2 systems divided in 2 different PCBs. However, this is not always the case. In IRASU, actually, it was a single board system like we want to do. However, this was manufactured by GomSpace, and the main drawback is that it is not open source, which we want. And we really like the work done by the people at Vision Space Technologies, but we really like the idea of having a comms system or basic comms systems embedded into the OBC. So that's what we want to do. We actually got in contact with BST, and they gave us some very good development advice. But yeah, we want to improve or modify their design and take advantage of all the PCB area available. And then finally, the software. My partner, Olman, is the one in charge of developing this and has been working for a while on his project, which is called SFSF. More information on that, hopefully next year, next edition of this Congress. But in short, it's a flight software framework with easy-to-use functions for telemetry, commands, scheduling or flight planning, and packet forwarding to different systems in the satellite. Well, this software is made to be cross-platform. Having a target hardware makes it possible to have interesting applications out of the box, which could leverage on functions like the second core and the MCU, and in general makes us more confident that we can launch a piece of hardware, not just a piece of hardware, but an actually working, easily implementable satellite module. So we are here looking for feedback for this idea. Well, we really like it. We want to know if it's something you guys will find useful. The current plan is for an early stage or mockup to be done for my undergrad graduation project, and the bulk of the development be done during a master's. So if this being a viable and interesting project is very important. So please send us your thoughts and opinions on the email on the screen, or you can scan that QR code to do it directly, or just speak to me in the chat or something. But yeah, I really want to know what you guys think and if it's something that would be useful to someone.
Amazing, Jaro, amazing. Thank you very much. So open source hardware, then there's soon a release. So please, everybody, turn on your microphone and give us the yes for Jairo from Costa Rica. You have 3, 2, 1. Yes! That's a big yes, Jairo. So I can tell you. So yes, please stick with the community. You're already on the channel, so keep everybody posted, and yeah, good luck for
Thank
everything.
Thank you very much, everyone.
Very cool. Next up is Montos.
So I'm challenging you to pronounce my last name right.
Yeah, I know.
Okay. Okay.
You have 4 minutes. I put your presenter so you can choose your presentation. With like thing 1, 0, 3.
Well, where's my presentation? I found it. Okay, so I'm starting my clock. So I'm starting. Like August 2019, we contacted from FOSA Systems, and they said that they had secure a position flying on the first flight of the Firefly, a new company launching a rocket in space, and they had secured a position for a flight that was meant to be March 2020. So they said that they want us to build, to put 2 Pico satellites inside and build also the deployer. We said that we are okay, we know how to build a deployer. We had no idea how to do it. So we took the opportunity to fly our first deployer and first open source Pico satellite deployer in space. We went through the ICD, and we hit our first milestone, which was to send to Firefly a mass dummy. So this was September 2019, less than a month to build a mass dummy, which meant to have the mass of the final deployer, and also the center of mass accurately by 1%, and also the moment of inertia with the same deployer. So we did some decisions on the first month. We had to follow through the rest of the project, and then we started testing and doing. This was supposed to be a video, but it's not. Okay, testing the rails, testing the release mechanism. This is October 2019 through the last in-person open source Cubesat workshop. And this is again testing, and this was the final design, and it was ready November 2019, and the first parts started to come in the shop, and this was a mix of the qualification parts plus plastic and 3D printed door made for testing again. And this was in my birthday, actually, 3 of December of 2019, so less than 3 months. This is the qualification model. We got qualified, and then we ordered the flight model parts. This is February 2020, and we built the deployer, went for qualification, again for testing, and we did by February 2020 we have complete everything. The deployer was ready to fly, and then we were waiting because the flight had some. Then COVID came in, and there were some delays, and then delays, and more delays, and more delays. And we finally shipped the deployer with the satellites at October 2020, almost a year after the project started, and like 6 months after supposed to be the flight. And then we waited again, and at September 2 of 2021, now a year after, it was the time for the rocket to fly, and then. This is the deployer inside the fairing, and 5 minutes after, at 15 kilometers altitude, this happened. So they said that we have another position, and we need to start this again from start. So this was the story about the first open source pocket satellite deployer, and we also make the second. Like the same one to fly the second flight, and also we build a new one, more lighter and more efficient. And yeah, if you want to follow us, you know where to find us. I'm Manthos from Libre Space Foundation. And yeah.
Thank you, Manthos. Yeah, amazing. So yeah, it crashes. That life, you know, c'est la vie. And you repeat again and do better. That's cool. Good philosophy. So for Manthos, everybody, please turn on your microphone. 3, 2, 1.
Yeah!
Yeah! Cool, yeah. I mean, an open source deployer. I mean, we need that. Thank you, Manthos.
Bye.
Is Manolis Surligas? I hope you're here. Yeah, you are. So, great. So you have 4 minutes, like everybody.
Yeah.
And I have your slides here, and I'll give you the presenter handle. Manolis, where are you? You're on the top, right? Oh, you could take it, right? It's okay.
I am now?
You are. Yeah.
Yeah.
So Manolis, 4 minutes. SatNOGS comms. What's the update? Thank you.
Yeah, sure. So, hi everyone. I'm Manolis from Libre Space. 2 years ago in Athens, we presented for the first time the SatNOGS comms project. And now I want to share with you some new stuff that we have done for all these 2 years that passed. So, what is SatNOGS comms? SatNOGS comms is co-funded by LSF and as a project. It's a UHF and S-band transceiver based on the STM32H7 MCU. It has also a Zinc 7020 FPGA on board, and is suitable for LEO missions for up to 600 kilometers. Of course, everything is open source and open hardware, and the key feature of this transceiver is the seamless integration with the SatNOGS network that we provide. Yeah. So the board will support FSK, MSK, BPSK, and QPSK for data rates up to 50 kilobits for the UHF and up to 1 megabit for the S-band. Based on the FPGA that it has on board, it can also support IQ data streaming, so everyone can implement their own modulation schemes or do more fancy stuff that, like, for example, spectrum monitoring or machine learning, etc. This is a rendering of the latest iteration of our board, but of course, we already have some prototypes right here. And we are doing currently testing to identify the RF performance of the transceivers and if everything works according to the plan. Here you can see the overview of the board. The RF front end is based on the 8086 RF 215 radio transceiver from Atmel. It has an onboard data storage and several other monitoring stuff that can be used for telemetry or to power down portions of the board. For the RF front end, the UHF can tune from 400 MHz up to 450. We cover the commercial bands, and but also the radio bands can be supported upon request. The TX power is up to 32 dBm with 1 dB step resolution, and the spectrum mask is compliant with the CFCG compliant regulations. The RF front-end interfaces have a custom ADC mechanism with custom low noise amplifiers and with quite high dynamic range. We have also implemented 2 different signal packs with different filter characteristics in order to improve selectivity if the user needs it. For the power management, we have 3 different power supplies and 1 rad hard FET in order to prevent any kind of latch up that can occur due to signal events during the in orbit. Of course, everything is monitored, and you can get these data through telemetry. The interface that divides is 2 canvas, full duplex, 1 SPI, and 2 interfaces for antenna deployment signals. All the board follows the Libre Cube specification regarding the PC 104 connector and the overall dimensions of the board. For the software, we decided to implement the control of the board in a dedicated, completely independent library based on C++, and we use a SimMake build system that you can build the entire firmware of the board using just SimMake and compiler. No external dependency at all, and no dependency on kind of custom IDEs or whatever. The MCU firmware is based on the FreeRTOS, but of course anyone using the libsatnogs library can implement it on his own RTOS, like for example CBIOS, which is very popular these days. For the FPGA, we have Vivado reference designs, and all of our IP cores are based on Axis.
2 minutes over, Manolis. Can you hurry up?
Sorry?
You're 2 minutes over the time.
Oh, okay. Sorry. So the availability will be due to this IC shortage. We believe that is for the second quarter of 2022, and the cost will be about 2,000 euros. So you know to find us, and yeah, thank you all for your attention.
Thanks, Manolis. You had like some kind of disconnections, but I hope that was only on my side. So thanks a lot for this SatNOGS comms board that is well weighted. Who wants to give a yes? You have 3 seconds to turn on your microphone. 3, 2, 1.
What did I say?
Yes! Yes! Of course, we want it. Great. So, Manolis, for every minute exceeded, you have to give 1 Bitcoin to an open source project of your choice. Okay, next! I didn't say that in the beginning, but it's a... Yeah. Thanks a lot, Manolis. You know where to find Manolis. He's on every channel, so reach out to him. It's good. Yannick is next. Yannick, are you there? You have turned on your camera.
Of course.
Oh, very cool. Very cool. So Yannick, I have your presentation around here.
Perfect.
So Yannick is a student. You're a student, Yannick, right?
Yes.
Student.
I will introduce that real quickly.
Yeah. Yeah, sure. So you're going to talk about encryption in open source Cubesat. That's cool. You can start talking while I'll give you the presenter right. Okay.
Okay, perfect. Well, hello everybody. Thank you all for coming to listen to my very quick presentation today. I will be talking about Cubesat cryptography, and more specifically about Cubesat certification, which is part of my research that I'm currently doing for my master's degree at ISE Supero in Toulouse. But first, I would like to talk about the question, why would we care about Cubesat cybersecurity? Well, as this graph that I got from the nanosatellite database clearly shows, is that the nanosatellite and Cubesat industry has been growing steadily and increasingly over the last couple of decades. That itself gives already rise to a lot of availability of software issues that I guess you all are quite familiar with, more than I myself. But what I like to focus on is the little red box that I highlighted at the bottom of the screen. The curve encapsulated by this box shows the amount of nanosats or CubeSats that have been launched with propulsion modules. And my question to you is, what do you think would happen if such a CubeSat gets hacked? Well, yeah, we get a missile, and that is of course not what we want. So one of the ways to counter this is by using cybersecurity and cryptography, and what we have chosen to do is to implement something called asymmetric public key cryptography. The idea behind this is that we use a key pair, a public and a private key, with which we can either encrypt, as you can see in the left side of the screen, or authenticate data. For purposes that I will explain more clearly later, we have chosen for now to focus fully on the authenticate data set, and the encryption data, the encryption of the data can be done in a similar manner another time, maybe for next year for this workshop. So authentication, what we did is we used self-signed digital certificates, which basically follow a very straightforward pattern. You have data from which you compute the hash, also a fingerprint of the data. We encrypt that using very complex and predefined cryptographic functions. That signature we mix with a certificate, and then we have a digitally signed certificate. We send this along with the data to the ground, and then on the ground we verify the certificate. We take the data, we compute the fingerprint and the hash, we take the signature, we decrypt it, and we compare the two. Are the fingerprints the same? Then that means that our satellite is the one that really sent this data, so we can prove the authentication of our data. If not, that means that someone has been trying to intervene with your data, which is of course not what we want. Well, currently there have been a few examples of mostly universities trying to implement similar things, but what you will see is quite often than not, for example here for the Norwegian or the Singaporean CubeSats, is that they are using symmetric key distribution. And the problem with this is that you cannot do authentication, which is exactly what I am currently working on. And otherwise you would have, of course, large satellite systems, which have been using this system for a long time. But not really within CubeSats of nanosats. And that is why we found this particularly interesting to do research in. So currently we are using the Mbed TLS library, open source, from Armbed, for which we can take generate key pairs and self-signed certificates. Then the next steps, what do I want to do to complete for this specific research is I want to implement the verification. I've now made the certificates, now I need to verify if they really work. I have to test them on ground. Then we will embed them into the Z board. This one we chose specifically because it has an architecture quite similar to that of the Nano satellite board. We have to benchmark our performances to see which cryptographic function works the best. Then we want to, if we have time, we want to embed it into the Nano board. And then in the end, we will publish our final results. And that's it for me for today. If you have any questions or want to know more about this topic, feel free to contact me. My email is here and you can find it in the abstract as well.
Super, Yannick. Thank you very much. So yeah, on board encryption. So turn on your microphone, and for Yannick, you know the game. So you have 3, 2, 1 second to give me your yes. Yes! Of course, encryption, right? So keep in touch. You know, it's always useful when you're doing a blockchain project. So next, Jan Peter, I'm taking presenter, choosing your presentation. So Jan Peter is actually a contributor to the Polaris project, and where is he in the list? Is going to speak about the open source space podcast, right? So it's good to have those kind of topics here. Jan Peter, I don't find you in the list. Why Jan, Mass, Jan Peter, and then disappear?
I'm sure I'm somehow over there, right? So
somewhere,
because I can see myself.
Start with a space, no? Okay, great.
Yeah, I'm very glad that I'm able to finish up today. I know we have a wrap-up session,
right?
But I'm the last talk tonight. So yeah, everyone, I just want to give you thank you. I won't need them. It's really just a brief update. I can elaborate any further, but I'm just here to give you an update on the open source for Space podcast, a project I launched last year. And just for starters, just a small recap, what is the OS2? The OS2 is an audio podcast where I want to interview basically everyone who's dealing with open source in space and doing a project or contributing otherwise or using it or something else. So everywhere where it's a link between open source and space, I want to have a talk with them and just to give them a stage for us. And of course to learn about them myself. So 1 year has passed. What happened? Nothing. So I did something, but nothing more. It stays with something. So I created a website. I created the Twitter feed, and I did the first recording. So this is the trailer. You can listen to it now, and I will show you in a second where you can listen to it. It's a 2-minute extensive analysis of what I have in plan, what I have planned for the podcast, and what you are be able to listen to in the near future. Yeah, well, there are there are 3 big podcast directories. The podcast directory is that thing where the podcast player on your phone or your desktop PC or whatever gets the feed from, so that it basically knows which episode is out there, which are possible to listen to, and which one wasn't used. And there's the German one, feed. It's a German base, but it's used all over the world. Well, I'm listed there with the podcast. The podcast index is a fairly new one, but quite a big one directory. Also listed myself, or listed the podcast. But Apple, I don't know. They say they published the podcast, and I refreshed like every minute today to maybe slip it in right before the talk. But apparently Apple, I don't know. Apple is interesting because they have the Apple Podcast Directory, which is like mostly used by most podcast players. So that's quite sad. But I can see it because I'm in the background. I have the special links, but it's not open for everyone. So, but many podcast players say the open source one. They use the other ones. But of course, Amazon and Spotify, they're not open, so I won't use them. You have found them. That's quite nice. You have always the chance to add them manually. So every podcast player has the chance to add a feed directly. You can copy the link, make a photo of the QR code, whatever you can choose. So for now, the best option I think is the link. So then you are independent from your podcast player. And I want to close with a small lesson learned. So when it comes to creating, I think a good plan is always better than no plan. But even better than planning is actually doing. So I had quite a sophisticated plan on how to do all the things with multi-track recordings and all the things. And I ended up doing barely nothing because of stuff. And so I think actually doing is even better than planning. That's all from my side. Yeah, we have here the links for the Element chat and myself, and you can. There's the Twitter feed for the podcast, and of course the website os2.space, and the beautiful logo.
And you have plenty of people to interview here, Jan-Peter. So
yeah, well, since you. I have a list. I have a few extra slides, and I have
wait for you. Yes. All right.
Oh, sorry.
No.
I just assumed.
Yeah, no problem. Okay, everybody. So for this podcast that Jan-Peter wants to do, and now everything is ready, and he just has to interview. Give me your yes. You have 3 seconds. Turn on your microphone. 3, 2, 1.
Yes!
Of course.
Thank you very much.
You already have all this in your list. This is cool. Thank you very much, Jan-Peter. Okay, we'll follow you on AntennaPod, open source.
I'm there.
I've found you there. Yeah, it's perfect. You're listed. Great. Thank you, Jan-Peter. You can stay up if you want. I mean, it's okay. All right. So this was the lightning talk, which is actually closing our day today. All right, Arthur, where are you?
Yeah, I'm here.
All right, good. So we've been through 3 sessions, lightning talk, and a keynote. I think we've seen many things today. You know, from satellite event detection as their servers, all the Orsat suite, how to analyze your mission, design your mission, IPFS Tiny, and those kind of things. SatNOGS, of course, and lightning talks that you just seen. And thanks to Pauline for how that works at Cali Poly and plan your mission. You don't have to send it. That's the good thing. The fun part is making the Cubesat. So unless you have an amazing mission, just send it. And now you know you have, I hope you made the connection you wanted to do today. You have Jan Peter who wants to interview any of you with an open source project. So do not hesitate to reach out to Jan Peter. And this is the wrap up. Arthur, anything to add? I'm sure you have something to add.
Yeah, wrap up. I mean, this goes very well with the season, right? You're wrapping up presents, and now we're wrapping up day 1. Nicely with a tie. And I don't have really much to say, but I would like to see the slide again with the world map. It would be interesting to see if we shifted maybe geographically in terms of audience participation. Maybe.
Yeah, we'll add it.
And I've seen that throughout the day, we had something like 60 to 70 people constantly connected. Of course, people coming in, going out. But yeah, we had a stable number.
That was nice. I want to thank everybody who is organizing. I mean, this is amazing. Thank you very much. Even like the contingency actions to have the audio of the people presenting docs. I mean, we went through satellites almost to get everything, and yeah. So I'm uploading the warm-up so we can get the map, because now we are UTC late. We have more people from like Tokyo or the other side. So I think it's slide.
So it would be great also if the committee members turn on the camera. We can you can come up stage.
I turn on my mic, but you can point where you are at the moment right now. We did that this morning. I hope we had a screenshot, and then we can compare. Montos, thank you. A lot of people in the sea. Mexico. Who's in Mexico? Jamaica.
Very good. Okay.
Hey, look in Africa over there. Is it South Africa or?
I also wanted to mention that I checked the participants list in before, and there was a Tesla participating. I knew that they're building smart cars, but I didn't know that those cars are so smart that they're even attending the Cubesat workshop here. Amazing. But it seems to have run out of battery. It's not there anymore. So
It went to recharge, I think. It's,
let's also do the following. Let's everyone turn on the mic and we take a group picture. And
turn on the camera for the group picture. Yeah, it's good.
Exactly, not the mic.
Some people have a very visual voice, so you could. It's okay. Cartago.
Cartago.
You can write.
Good. Everyone's still fresh.
After that, we have the Hangout, right? The online social event. We?
Indeed.
Right. It's
Okay. More cams, come.
we're 52. How many zombies? Arnold.
12 now. We can do more. We can do more.
Where is Daniel? We don't see you, Daniel. Ah, pretty nice. Dino, Dmitry, Douglas, Frank Zippenfeld. Where are you? I'm calling the name, by name, so they feel like obliged. Mario.
Fernando.
Omar, Victoria. You were amazing at drafting everything this morning. People are here since this morning. Thank you very much. This is amazing. I hope next year we can do it like in person, but I feel like we have to keep the remote one. So because some people are very in areas where it's very hard to get out from, and also it's very hard to get a visa to get anywhere else. So yeah, unless we can make visas on the blockchain on satellites.
The funny thing it was also that we, since we hosted it last year and online, we expected it to be the one and only online event. So that's why we didn't take any notes, right, on how to set up such a server and how to stream. So we kind of had to rework all that.
But I think you did a fine job.
But I think this year is last time. We don't need to take any more notes here.
So group.
Okay, so I'm taking a screenshot now. 3, 2, 1. Good. Okay, we are actually, good in the time, over the time. And let's call it a day, officially. So that means we're going to switch off now the recording and the streaming, but we leave the room open. And what we're going to do, exactly, you can see the slides. I'm going back to the slides. Take presenter. Wrap up. Next slide. So, okay, I'm stopping the recording now. Everything.
Oh, Yaro, people are asking for some tamales. What is that?
Is that some kind of glühwein or glöck or something?
I think it's mate or something like that, no?